ঠিক ঠিক ঠিক।
And Naranda, welcome.
22 জুনটা
কেমন আছেন? আনমিউট করুন, আনমিউট করুন।
আনমিউট করুন।
And Naranda,
22 জুনটা
কেমন আছেন? আনমিউট করুন, আনমিউট করুন।
আমি আনমিউট করেছি তো। ও ফ্লুক
এখন শোনা যাচ্ছে।
ইউটিউব লাইভটা চালু হয়ে গেছে। হ্যাঁ,
ওকে,
এই পূর্ণবোধ কি আমার কথা শুনতে পাচ্ছেন?
হ্যাঁ ক্লিয়ার।
হ্যাঁ হ্যাঁ, অনির্বাণ ইউটিউব,
আচ্ছা হ্যাঁ, আমাকে বলো আমার সাউন্ডটা আবার কি প্রবলেম হলো?
অনির্বাণ ইউটিউবটা কি স্ট্রিমিং আরম্ভ হয়েছে?
চালু হয়ে গেছে, ইউটিউবটা চালু হয়ে গেছে।
আমি এখনো দেখিনি।
আমরা পুরোটাই, হ্যাঁ আমি বলছি, আমরা চেক করে নিয়েছি। ইউটিউব লাইভ স্টার্ট হয়ে গেছে, সুতরাং এবার তুমি শুরু করে দিতে পারো সময় হলে।
আচ্ছা দুটোই বোধহয় খুলে নিলে সুবিধা হবে না? আচ্ছা, আমরা কি ক্যামেরা এমনিতে অফ রাখবো তো?
হ্যাঁ, ক্যামেরা এবং মাইক্রোফোন দুটোই আমরা অফ রাখি।
হ্যাঁ, কিন্তু যখন তুমি যে কথা বলবে সে তখন মাইকটা অন করে নেবে,
স্পিকার অন করে নেবেন, মাইকটা খালি,
ক্যামেরাটা অন করে নেবে।
না, এমনিতে কথা বলার সময় কি ক্যামেরা অন করা দরকার আছে?
হ্যাঁ, তোমার যে ইন্ট্রোডাক্টরি স্পিচটার সময় তুমি অন করে নিও।
আচ্ছা ঠিক আছে, তাহলে আবার জানলা ফান্না খুলতে হবে। এই রে,
সবাই কি যে যার বাড়িতেই?
আমি অন্যদিন ডিপার্টমেন্টে চলে যাই, কিন্তু অনেক সময় ওখানে কারেন্ট অফ হয়ে গেলে ইন্টারনেট সব বন্ধ হয়ে যায়, ফলে সেই ভয়ে আমরা এসে যাইনি।
নারায়ণদার ভয়েসটা একটু কম লাগছে।
আচ্ছা, একটু বাড়িয়ে নেবার চেষ্টা করছি। ঠিক আছে, এবার ঠিক আছে,
একদম একদম।
শ্রীরূপ কেমন আছো?
নারায়ণ বরাবরই মৃদুভাষী।
ভালো আছি নারায়ণদা, আপনার কি খবর?
আমিও ঠিক আছি, চলছে।
আপনি অ্যাপিয়ার করুন একটু, আপনি ভিডিওটা অফ করে গেছেন তো?
হ্যাঁ, ভিডিওটা
হ্যাঁ, এই তো দেখা যাচ্ছে এবার। না, আমিও বাড়িতেই, অফিসে গেছিলাম।
না, আমি অফিসে গেছিলাম, কিন্তু এইটার জন্য বাড়ি চলে এলাম। আমি এইটা আবার অফিস থেকে করতে পারি না।
তাছাড়া মাস্ক পরে এটা করা খুব মুশকিল।
হ্যাঁ,
তাই বাড়িতে আরাম করে বসেই করা যায়। মানসকেও দেখছি, পারঙ্গমা, আর একটা কাকে দেখলাম জানি, অনির্বাণ, বিভাস।
হ্যাঁ,
আনফরচুনেটলি আমাকে কেটে পড়তে হবে, আমাদের আবার একটা মিটিং সাইমালটেনিয়াসলি এখন আছে। কালকে ছিল, আজকে মানে কালকে পোস্টপোন হয়ে সেটাকে আজকে করবে।
কি বাবা,
অভিজিৎ দেখছি,
এসে যাবো একটু পরে, চলে আসছি।
ঠিক আছে।
নারায়ণদাকে অনেকদিন পরে দেখলাম, ভালো আছেন নারায়ণদা?
হ্যাঁ হ্যাঁ, অনির্বাণ কেমন আছো?
চলছে আর কি।
কিন্তু নারায়ণদা ভীষণ রোগা হয়ে গেছেন।
একদম।
না না না, অতটা নয়, অতটা নয়। চশমা খুলে কিছুটা ওজন কমেছে, এটা ঠিকই, সেটা ভালোই হয়েছে। কিন্তু
এমনি ঠিক আছেন তো, কোনো প্রবলেম নেই তো?
না না, এমনি ঠিক আছে। তোমরা সব ঠিকঠাক আছো?
এখনো
সময় যেমন থাকা যায় আর কি।
আমরা তো ইউটিউব লাইভ স্ট্রিমটা কিন্তু লাইভ এখন।
হ্যাঁ, তো
কেমন আছো?
অরুণাবদা, অরুণাবদা,
চশমা খুলে একটু লাগছে, চশমাটা পরে থাকলে দেখতে অসুবিধা।
I am closing at 82. হ্যাঁ,
ঠিক আছে, ঠিক আছে, 85 অবধি যেতে পারো।
আচ্ছা
আচ্ছা, অনির্বাণ, এখন ইউটিউবটা যেখানটা চলছে, পরে আমরা যখন ওটাকে একটু এডিট করে নেবো। হ্যাঁ
আচ্ছা, না সে তো করে নেবো, কিন্তু পার্টিসিপেন্টরা কি ইউটিউবে অলরেডি ঢুকে পড়েছে?
হ্যাঁ, দেখতে পাচ্ছি তো।
আচ্ছা,
সেটা একটু অনেককেই দেখতে পাচ্ছি আমি।
হ্যাঁ আচ্ছা, হ্যাঁ তাই তো বটে। তাহলে কি আমরা শুরু করবো নাকি একটু দাঁড়াবো? কারণ কজন টোটাল?
59 বাজে, 3:55 বাজে, আর 1 মিনিট পরেই শুরু করো।
আচ্ছা,
আমরা আমাদের শিডিউল অনুসারে চলবো অনির্বাণ।
চলবো। আসলে ক্যামেরাটা অন করে জিনিসটা পড়তে গেলে কেমন টেরা টেরা দেখাবে, আমি তাই ভাবছি। আচ্ছা দাঁড়ান, কি দিয়ে করতে হবে? আসলে আমি একটাতে ইউটিউব লাইভ স্ট্রিমটা খুলেছি আর একটাতে এইটা খুলেছি, তারপরে আমি যেটার দিকেই তাকাই আমাকে টাটা টাটা লাগছে আর কি।
অনির্বাণ, তুমি গুগল মিটের যেটাতে খুলেছো তার ক্যামেরার দিকে তাকাও।
হ্যাঁ, তার ক্যামেরার দিকে তো
সেখানে তুমি তোমার সেই স্ক্রিনেই তুমি তোমার লেখাটা খোলো, তুমি তো স্ক্রিন শেয়ার করছো না।
স্যার শুরু কিন্তু স্যার।
ও হ্যাঁ, আচ্ছা আচ্ছা, স্ক্রিন শেয়ার তো করছিলাম, সেটা
চল স্টার্ট কর।
এটা স্টার্ট।
Okay, good afternoon. Am I audible?
Yes, you are. Anirban.
Okay. Yeah, good afternoon. On behalf of the Department of Physics, West Bengal State University, I welcome you all to the national webinar, History of Science and Indian Perspective, where we shall celebrate the life and works of two Indian scientists who, through their work, have helped put India in the world map of science. We have two speakers for today's program, Professor Narayan Banerjee from IISER Kolkata and Professor Srirup Rai Chaudhuri from TIFR Mumbai. We are about to begin, but before that, let me request you to keep your microphone and cameras off while the session is in progress. I also request those joining via the Google Meet to place their questions in the chat box during the lectures. Besides the participants joining over the Google Meet, we have a lot of people joining through YouTube live stream also. So I'll request them also to put their questions in the comment box in YouTube. These questions will be put forward by the moderators to the respective speakers after the talk is over. Please note that if someone gets logged out of the Google Meet due to some connectivity issue or some other technical snag, do not hesitate to rejoin. If you encounter any problem in joining the Google Meet, there is always the YouTube live stream which you can join, and you can find the link for that in the WhatsApp group created for this webinar. Link to a Google form will be provided in the WhatsApp group at the end of the program. Kindly fill out that form so that we can prepare your certificate of participation. We have the wishes and support of our Honorable Vice Chancellor, Professor Mahua Dash, but she has a meeting with the Higher Education Department today going on at the moment, so she will not be able to join with us for today's program. So anyway, I now request the senior most member of our department, Professor Dr. Orunabha Adhikari, to take the session forward and introduce the first speaker. Orunabha.
Thank you, Anirban. So, today's webinar, I must say, is a star-driven gathering. In physics community, we also have our own stars who have mesmerized us with their research and their teaching and their personalities. Today, we are proud to have two such brilliant scientists and teachers among us, Professor Narayan Banerjee and Professor Srirup Rai Chaudhuri. Both of them are known to most of the participants of this webinar. They actually do not need any introduction, and therefore, it is merely a formality. Our first speaker, Professor Narayan Banerjee, studied physics honors in Presidency College and obtained MSc from the University of Calcutta and PhD from Jadavpur University. He was a faculty at Sharad Centenary College, Dhoniakhali, Hooghly, Sripad Singh College, Jiaganj, Murshidabad, Jadavpur University, and presently he is in Indian Institute of Science, Education and Research, IISER, Kolkata. His research interest is around gravitation and cosmology, presently working on several fields like one, model of the dark energy, the driver of the alleged accelerated expansion of the universe. 2, quantum cosmology, and 3, problems on gravitational collapse and formation of black holes. And during 2002 to 2004, he was secretary of the Indian Association for General Relativity and Gravitation. Later on, during 2012 to 14, he was again president of the same organization, Indian Association for General Relativity and Gravitation. And we are very happy that presently he is a member, honorable member of the Postgraduate Board of Studies of our department. So, Professor Banerjee will now talk on N-Sirana, a comet in Indian astrophysics. Professor Banerjee, please.
Thank you, Orunabha. So I thank Vibhash for inviting me for this webinar. So I am not really too comfortable in these webinars, particularly when I'm talking. In one such meeting, I had to send my talk to the organizer and who showed it on my behalf. And I could somehow manage to speak on that. Incidentally, that was on the same subject, on Narayan Chandra Rana. So Bibhash said this is his topic and he wanted me to talk on Narayan Chandra Rana. So first he said that this is our theme of the thing, and Srirup Rajchoudhury will give one talk and you give another talk. I said that I shall not be able to prepare a talk in this short notice. Then he said, talked about this. So I agreed, because this is really, I mean, many of my friends said that the new generation of young physicists hardly know about Narayan Rana. So it's really worthwhile to introduce, to give a talk on him. So I shall just now share my screen. So is it visible?
Perfectly visible.
Yes.
Okay, thank you. Thank you. So, as I said, the topic is Narayan Rana, a comet in Indian astrophysics. I'll explain why this name is given to this talk. So, Narayan Rana was born in 1954 and passed away in 1996. So that explains the title of the talk. So he was short-lived. He passed away at the age of barely 42. But even in this short span of life, he did a lot of work, not only formal research, but also in popularizing science, astronomy in particular, but science or physics in general. Narayan Chandra Rana, popularly known as Rana in the community. In the astrophysics community, people normally called him Rana. And I was somewhat junior to him. I came across him during 90s, early 90s, when he joined IUCAA. So then we developed a kind of friendship, and whenever I visited IUCAA, I made it a point to visit him at his home. And he will remain as one of the brightest scientists in Indian astrophysics. So he did not live long, as I said. So sometimes he is referred to as a comet rather than a star. Narayan Rana, his education, he started his education in Shauri Bholanath Vidya Mandir. He did his school final there. So this was in a village in Midnapur district, a very distant village, and hardly known. But he stood first in the school final examination from that school. Then he joined Presidency College, did his BSc from Presidency College, and did his MSc from Science College, Calcutta University College of Science. So he was a very bright student during his BSc, and all the teachers in college were very fond of him. I know the relation between Ranada, I called him Ranada, and Professor A.K. Rajchoudhury, and I saw that in 90s when Ranada visited Jadavpur University and gave a talk. So I shall come back to that later. He did his MSc in Science College, and then he went to TIFR for his PhD. There he worked with Professor Jayant Vishnu Narlikar. So after his PhD, he spent a short stint at Durham, UK as a postdoc, and came back to TIFR. So he started his career, professional life at TIFR itself, and then when IUCAA is formed in 1989, with Narlikar as the director of the institute. After some time, in early 90s, 92 or 93, he brought several of the stars then Ranada should have been called a star, but now a comet because he did not live long, but to Ayuka. So he was at Ayuka till his death. So in his school, he started his career in astronomy, in fact, in the school itself. He was deeply influenced by his teacher, Monindra Narayan Lahiri. Monindra Narayan Lahiri was a gem of a teacher. He influenced many students in the village and also in some other villages or areas in the district. He was particularly interested in astronomy, and he, with his enthusiastic teaching, many students, including Narayan Rana, was involved in the night sky observation from his school days. So Narayan Rana also developed interest in science in general, and as usual, in astronomy in particular during those days, as I already said. So in fact, as a school student, he made some telescope and helped his friends watch the sky during the night in the village. So now I shall come to somewhat technical things. His research, he had a very widespread interest in astrophysics. So his main research area was astrochemistry, and this was right from his PhD days, and this did last till the end. But early interest of Narayan Rana in research was to show that the compatibility of Hoyle-Narlikar theory with CMDR. As the specialist would know that Hoyle and Narlikar gave a theory of or a model of the universe, which is called the steady state model of the universe, which in order to avoid the singularity in the standard Big Bang model, the idea is the universe has a very steady kind of state, and although we see it expanding, but actually there was no beginning of that. But the main problem of this steady state theory is with CMBR. It does not account for the cosmic microwave background radiation. So Narayan Rana's early attempt was to check whether this CMBR is compatible with steady state theory of Hoyle and Narlikar. But as I said, his main research interest was astrochemistry, and he started this project with Narlikar and SM Chitre at TIFR. And this interest remained till the end, as I already said. He later worked on the estimation of molecular hydrogen in the galaxy and the chemical evolution of our own galaxy. The second work, he worked with Wilkinson. Wilkinson was his PhD student, in fact. And then he also worked on, in this astrochemistry thing, the distribution of metals in stars, particularly the dwarf stars, white dwarf or other dwarfs. This he did with Basu, and Basu was his another PhD student. So this was his early interest, which remained till the end. As you see, he worked with astrochemistry with his PhD students as well. The other research interest was in cosmology. The main thing was to show that CMB requires astrophysical inputs, and through this, he wanted to connect steady state theory with CMB. He was also interested in varying G cosmology. So there are some theories, relativistic theories of gravity, other than general theory of relativity of Einstein, where the Newtonian constant of G is varying, is a function of space-time coordinates rather than being a constant. So Rana was interested in this varying G cosmology as well. He worked on several problems of this varying G cosmology. He was also interested in high-energy astrophysics, and in this his main interest was in X-ray sources. So this was his main research interest. He also worked on stellar astrophysics, and this work is very important, highly cited work on the role of initial mass function in the formation of stars. When a star forms, it starts from a local perturbation of otherwise uniform density, and for the formation of a star, and the initial mass profile is required. So his work was on this initial mass function in the formation of the stars, and this was particularly in reference to the spiral galaxies. So so as you can see that he had a very widespread interest in research, although whatever I have said all are in astrophysics, but in astrophysics he did not confine himself to a very narrow area. He had indeed a very widespread interest. He also worked on, outside astrophysics, he worked on celestial mechanics and wrote a book on that. So I can also tell you about his widespread interest in research. He gave a talk at Jadavpur University. We had a center of relativity and cosmology research center in Jadavpur University. Rana gave a talk when he was at TIFR at Jadavpur University on the oscillations of the galactic plane and connected it with the extinction of dinosaurs. So this was the research interest of, the wide variation of the research interest of Narayan Rana. He also wrote a few books on physics. One is on classical mechanics, and the other is on our solar system with Joshi. And the classical mechanics book was written with Pramod Juag. So I shall spend a couple of minutes on this classical mechanics book. This classical mechanics book was written as a follow-up of the coursework at the University of Pune. While at TIFR, Rana taught a course on classical mechanics. And Rana and Juag, one of them taught, in fact, Rana taught it, and Juag was his teaching assistant in this course. And they both decided to work on a book on this course. So this book, today's students know Narayan Rana only through this book. So I shall spend a couple of minutes on this. This book is definitely very different from other classical mechanics books. In what respect? So it has the formal structure of classical mechanics. It deals with various things as a standard classical mechanics book will do. But where is the difference? Look at the problems. So the problems are related to various things from life, and mainly from games and sports. Cricket, football, running, jogging, getting upstairs, even sleeping. And also on various other things, like he related the viscosity Cauchy equation with the radius and length of the tube that he required for a bypass surgery, in cardiac bypass surgery. So these kind of problems are included. And also some rough estimates of gravitational collapse or the cosmology and things like that are also included there. So this is a very, very interesting kind of a work by Narayan Rana. And I am not introduced to PC Juag anyway, but I knew him, and I am sure he did not have any reputation as a sportsman, or even he was not known as a great sports lover. But still, the book is like that. So one student will always be interested in solving those problems. So I shall also say another thing about this book. Given the job of teaching classical mechanics at that level, meaning first year MSc or an advanced undergraduate, I shall always advise the students to solve the problems given in the book, but as a teacher, I shall not use that book as my mainstay. I shall rather use some other standard text like that by Goldstein. Why? If one knows Rana, he will see his face through the pages. So if one wants to teach classical mechanics, as for myself, I would rather want to teach it myself. So his personal attachment with the book is writ large at every page of the book. Our solar system is also a very nice book, which is also used by many universities where this as a part of their course. But Rana's another main interest was in outreach. So he took very keen and serious interest in outreach. So when he joined, Ayuka started an outreach program. So he chaired the outreach committee, and the members of the committee included Jayant Narlikar himself. But Rana was the chair, and with the help of Arvind Paranjape, he did several very important work in this business. Ayuka's outreach is still very famous. It has a park, astronomy park, and also other many programs in outreach. Every year they have school children visiting their institute, showing various things in astronomy. Also in the year of physics in 2009, much later than Rana passed away, Ayuka organized many telescope making workshops for school children throughout the country. And all this outreach program was started by Narayan Chandra Rana. And he wrote enormous number of books and pamphlets for non-experts, particularly pamphlets. And also, he was very serious about this outreach because his idea was, we are doing astrophysics or astronomy with the help of taxpayers' money. So we should go back to the taxpayers, the public in general, to let them know what we are actually doing, what the science is actually all about. This science is all about. And he knew that this requires a concerted effort. So an individual cannot do this. So he was instrumental in setting up the Confederation of Indian Amateur Astronomers, which did a huge job in spreading knowledge in astronomy and astrophysics. So, say he took up a project with the help of school children, mind you, in 1995 total solar eclipse, the project on the measurement of the radius of the sun during the solar eclipse. And this project was meant for school children. Yeah. So, as a person, he was very generally soft. He was very soft-spoken, and was not too comfortable in all sorts of adda, I should say. And he used to always keep a very low profile. He, whenever required, he never failed to complain about things which are not correct. But normally, he always kept a very low profile. But in one thing, he was always very generous. That was about discussing science with all kinds of friends. Mind you, all kinds of friends. With little kids, to his classmates, to serious scientists. His health was very poor, and he was in trouble whenever. In fact, we knew that his health was poor. He had a serious heart disease. He had a heart attack when he was a PhD student at TFR. And Narlikar was instrumental in getting him hospitalized, for helping him in having the surgery, and so that he can lead a somewhat normal life. But actually, this was not really known to many of his friends. This problem was actually there from his student days. When he was a student in science college, he was in problem when the elevator was not working. And I can see many of my friends in this audience did their MSc in science college, and they would remember our second year class was in the first floor, only in the first floor, but he was in trouble. I would rather say that Narlikar actually allowed him to work from home while he was at Ayuka. But he had a failing health, not only for his cardiac problem, but also other kinds of problems. He had all sorts of physical trouble. He was in a kind of trouble with his digestive system. All the time he had ill digestion and things like that. So seldom he came to his office at Ayuka. He always worked from home, and his students used to visit his home. Fortunately, the home was in the quarters in the campus itself. So I have a hunch that Narlikar somehow anticipated that this boy will not last long. So let us allow him to do his work as much as he can contribute. So he passed away at the age of 42, but even before that, he contributed so many things in science, in astronomy, in serious research, and also in popularization of science. So I would add one incident. This I learned from Bhupatida. Bhupatida is a well-known person in physics. He used to teach in Chagda College, but he is retired long back, some time back. So Bhupatida was his Narayana's classmate for MSc, and he said that they went to Voltaire Science Congress together, along with their teacher, Professor Bhattacharya. And I would not say the name. There are many Bhattacharyas in Science College, and they teased him during the train journey. And another, to start with, was hesitant, but then joined his friends and did that. And also, I would say that he had a never-failing interest in night watching, and he used to train anyone whenever asked for. So, the other thing is, he had a very nice and cordial relation with his friends. And when he was in TIFR as a faculty or later joined Ayuka, sometimes when he came to Calcutta, he never failed to call his old friends like Bhupatida and others and made it a point that they would meet some time. He also had a deep sense of gratitude to Ramakrishna Mission because Ramakrishna Mission helped him in his education. He came from a very poor family, and Ramakrishna Mission helped him in his education to a great extent. So in this connection, with deep gratitude, the sense of gratitude, I would talk about an incident, an anecdote. When he came to Calcutta, Jadavpur, for giving a talk, as I already mentioned, on the oscillation of galactic plane and the extinction of dinosaurs, So in our relativity center, Professor Amol Rai Choudhury was connected with us. So he was an honorary professor in the center. So when Rana saw AKR, he just lied on the floor and offered his pranam to him. AKR said, Rana, তুমি একই করছো, তুমি তো এখন অনেক বড় হয়ে গেছো, এখন এরকম করতে হয় না. But he never failed to do that whenever he saw AKR. So with that, I shall conclude my talk, and but I shall also tell you about some of the references. There is a very nice piece of work in Sirana, His Life and Contributions by Utpal Mukhopadhyay and Shoibal Rai in astrophysical sciences. This was published in the Indian Journal of Science, and the reference is given. And also, there is a very short essay by K. Abhayankar, who was the administrative officer of Ayuka, remembering Dr. Narayan Chandra Rana. And also, I'm personally grateful to Dr. Bhupati Chakraborty, as I already mentioned, for some of the stories about Narayan Rana during his student life. I think I shall stop here, but I shall wait for questions. If you have any, you can easily ask. Although I'm not sure I shall be able to answer them or not.
Okay, Molidi, are you there? Molidi, are there any questions from the Google Meet side?
Yeah, Dr. Shah, sorry for the delay. Yeah, I'll just check. Thank you, Professor Banerjee, for a very illuminating talk on and introducing us to Mr. Rana. So I'll just check whether we have questions. We don't have questions, any questions in the chat box yet. So Dr. Shah, do you have any questions there? And
I myself have one or two questions, but let me first convey some questions from the chat box. I have one or two. Deepon, who is one of our students, our MSc students, he is asking that that FLRW cosmology was already known. So how was Professor Nalikar working on a steady state theory? Because he is under the impression that there was some, expansion of universe was already known at that time. Can you elaborate a little bit on that, Narendra?
Well, FLRW cosmology, that is a solution of Einstein's equations, right? But how do you know that that is the actual model of cosmology? I would say two things. One is that with the creation term, you can arrive at Hoyle-Ehrlich's steady-state version from Einstein equations, where the metric is given by FLRW. FLRW is a very, very general kind of a metric. With the scale factor, the solution of the scale factor you have to arrive at from Einstein's equations. And Hoyle-Ehrlich's steady-state model, you can arrive at the Hoyle-Ehrlich's steady-state model even as a solution of Einstein's equation using FLRW metric. So it was not different. So the Big Bang model is a different model based on the same FLRW metric, where you have a singularity at the beginning. I think that answers your question, because FLRW is not competing with Hoyle-Ehrlich theory. Hoyle-Ehrlich, I should say Hoyle-Ehrlich model. So FLRW is a metric which gives you the space-time geometry, but not the exact solutions. The exact solutions you have to extract through your ansatz on the matter distribution, and steady-state model and Big Bang model, they are subsets of this FLRW cosmology.
Okay, I hope that answers it. I myself have another question, which is, you said something about a variable G cosmology that Professor Rana was doing. So is that this varying G has something to do with Brans-Dicke theory of cosmology?
Not really only one. It was not really Brans-Dicke. It was something else, but some other non-minimally coupled theories he was working on.
I mean, in general, scalar tensor.
In general, scalar tensor kind of theory.
Okay, but back then this expansion theory was not there. So
The expansion.
what was,
Sorry.
I mean, this expansion model of the universe, that is this accelerated universe, etc. This is
Accelerated expansion.
not there.
Right, accelerated expansion was not there.
Not there. So what was the motivation? Because
right.
apparently we do that so that we can, take care of the dark energy thing and something like to bring that into picture. Dark energy or modified gravity, those sort of things are go parallel to each other. But back then, what was the motivation? I mean, I don't know what was the motivation for Brans-Dicke theory also.
Everyone, I shall love to discuss this with you, but this will be a bit slightly technical, I mean, compared to the level that I have spoken. But some of the friends will be interested, so I am trying to give some answer to this.
Yeah.
First of all, Brans-Dicke or other non-minimally coupled theories, historically, they did not originate from the accelerated expansion of the universe. In fact, Brans-Dicke theory was proposed in 1961. The idea was completely different. The idea was to incorporate Mach's principle in the realm of relativistic gravity theory. And many of the FR gravities, they are introduced in order to setting up a nice background for quantizing a gravity theory rather than anything else. Later, it was found that these theories give you a very nice place to work on with. I mean, even without any dark energy, you can explain this accelerated expansion of the universe. That is true. But I can also tell you the motivation of Narayan Chandra Rana. It was not driven by Brans-Dicke theory. This actually was originated from Dirac's large number hypothesis. Dirac constructed a few ratios which were dimensionless out of the natural constants, like capital G, Planck's constant h, speed of light in vacuum, and proton mass. Out of these kind of objects, he constructed several things which are dimensionless and showed that they have a value, definite value. If it is dimension full, then the value is not very important, but you can change your unit and have a different value. But the dimensionless numbers, the value is always will create some puzzle. For instance, the fine structure constant, which is 1 over 137, but it's dimensionless. So we are always curious why it is 137, why it is not something else. So Dirac's large number hypothesis had this kind of a thing where you can explain the large number hypothesis that this will be a constant if you have a varying G model. So that was the initial interest in a varying G cosmological model. So it is not that it has to be a function of a scalar field phi or something like that. So Rana's interest originated from Dirac's large number hypothesis.
Okay. Let me check if there are any other questions. Just hold on for a moment.
Sure.
Because okay. Okay. Another thing which actually I know, but let me just ask you anyway, because there are many students in the audience. That is when you mentioned about meta.
Anirban?
Yes.
I think we have a question from Sirubda. Sirubda, did you raise your hand?
I did, but I'll make that at the end. It's more a comment than a question.
Okay.
Okay. I'll just ask Narendra to just answer another just small thing for our students mainly, which is when you mentioned that Professor Rana worked on metals in stars.
That's right.
Right. So I know what this is, but I'll just ask you to explain this to us.
Narendra
What
says
we
the
mean
same
when
question from
chemicals.
me, from my side too. I'm a novice in this, but I would like to know what is the principle? How could Professor Rana work in this spectacular field called astrochemistry during his time?
So Oliver's question is related to that. Astrochemistry would mean the composition of stars and galaxies, right? So
Right.
as I mean, various stars, they do not have only hydrogen. They have other heavier elements, helium, carbon, and even metals. So Oliver's question is related to that. That is called astrochemistry. And Oliver's question is related to that, the metals in the stars. So you know the nuclear reactions, fusion reactions are going on in the stars, and they would result in heavier and heavier elements, starting from hydrogen to helium, and they will eventually form iron, which is the stablest of elements. And so there are many stars which are quite iron rich. So these, so you can find out from the temperature profile and other things the constituents of the stars, what they are made of, which metals they have. So this is the all about the estimation of metals in the stars.
Thank you.
Maruti, can you ask your question?
Yeah, my question was related to the same thing. Because I was interested in knowing as to where was this data collected from. Professor Banerjee just mentioned that it was from the temperature profile and all that, right? So, great piece of work. But I mean,
temperature and of course the color and other things.
Colors and all. Okay. Can we have that comment from Sirubda?
Yeah,
And,
well, it has really nothing to do with astrophysics. It's just to do with another aspect of Narayana, which was mentioned by Narendra here, which is that he worked closely with Arvind Paranjpe in setting up the outreach of Ayuka. Now, I wanted to say that Arvind Paranjpe is now the director of the Nehru Planetarium in Bombay. And it was at his behest and his request that I prepared the talk on SN Bose, which I will now give you. So for the SN Bose 125th year was in 2019. It was Arvind Paranjpe who sort of persuaded me to write up and prepare this talk. So there's a faint connection with Narayana. It's not a scientific connection, just a personal.
No, but Srirup, thank you very much, because Arvind is a very, very interested and enthusiastic man.
But
in fact,
yes.
During the International Year of Astronomy in 2009, he was instrumental in organizing telescope making workshops, 2-day telescope making workshops for school children.
I know that. But I just wanted to say that there is a little bit of Narayana faint thing there in my talk also, though it will deal with some completely different topic. Thanks.
Thank you, Srirudra. So, Anirban, I have
just one more comment to add.
Okay, please.
Yeah, the comment is this this science outreach program of Ayuka that I didn't know that Professor Rana had something to do with it. But when we first started this astrophysics astronomy course in our department, we had enormous help from Ayuka, and I personally visited there quite a few number of times. And I also attended one of those telescope and detector making workshops. And I'm just to let you know that this program is still going on, and they every year or every one or 2 years, Ayuka still organizes this telescope making and photo detector making projects, and they attract all college students or even faculties from colleges who can visit Ayuka and participate in the workshop and make their own photo detectors, and then bring that back along with them to their department so that they can do astronomy, observational astronomy. So that's just a side comment that I would like to make.
So, Anirban, thank you very much. So, as we have enough time, may I make a comment on that?
Yes.
So, yes, of course, what you said is right. But during 2009, they moved all over India to organize these workshops. The workshops are not only Ayuka.
Yeah, 2009 was the
year of astronomy, year of
year.
astronomy.
There was something like that.
And as you have mentioned, IUCAA still holds that, and still they organize workshops outside IUCAA. Samir
Yes.
Gurde is in charge of that, I
Yes,
think.
Samir is my batchmate in Pune University
I see.
program. So I don't know whether Naranda, you remember when I first visited Pune. I went there, and when I was about to get admitted in the MSc course, you were visiting IUCAA.
Yeah, I know.
I
was an associate,
along with my father went and met you there.
yeah.
We had some other personal connection. Anyway, so
I find some questions in the chat box. Can you please?
Yes, Narendra, I'll take a question from. Will you take a question from Shayon Khara, from one of the participants in the Google Meet?
Sure.
Yeah,
Sure.
Shayon, sorry to have kept you waiting. Please unmute yourself and ask your question. Shayon, are you with us?
Yes, ma'am.
Yeah.
What is dwarf star?
Dwarf stars are some stars which are much smaller in size than a normal star. For instance, there are something called white dwarf. White dwarf is a star where the nuclear reactions are all over. I mean, the star is dead, is exhausted of nuclear fuel. Then it starts contracting on its own gravity. But then what happens is that, this is technical, at some point of time, so there are the atoms in the stars, they are normally ionized, and the electrons, they are freely moving, they form an electron gas, and as you know, electrons are fermions, they form a strongly degenerate electron gas. And this electron gas will have a degenerate pressure. Degenerate electron gas will have a pressure. And this pressure can work against the gravitational collapse, and the star equilibrates at a certain size. So you can think about the size of a star. So, but a white dwarf, thus formed, will have, suppose there is a white dwarf whose mass is of the order of the mass of the sun. The radius of the white dwarf will be less than 10 kilometers. Will be less. So these are called these are called dwarf stars, which are much smaller than a usual star.
Okay, sir. Thank you.
So I don't have any more questions here on my side. Dr. Shah?
No, here also there are no more questions, I guess. So should we move on to the next session?
So if there are no more questions, Soniban, let us thank Professor Banerjee. Thank you, sir. Thank you, sir.
Thank you very much. Thank you very much.
Time with us. And if it's possible for you, please stay with us.
Yeah, I shall be staying with. I shall be interested to hear Srirup.
Okay. Thank you so much, sir. Thank you so much. So let us all thank Professor Banerjee, and I hand over the baton now to Dr. Odhikari. Dr. Odhikari?
Yes, I'm here.
Yeah. Please introduce the next speaker.
Thank you. Our next speaker, Srirup Raichoudhury, is a professor in the Department of Theoretical Physics, Tata Institute of Nuclear Physics, Mumbai. He studied physics honors at Presidency College and obtained both MSc and PhD degree from the University of Calcutta. He did postdoctoral research at SINP, CERN, and TIFR. He worked as a faculty in IIT Kanpur before his present position. Professor Raichoudhury is a high-energy physicist. He studies and tries to understand the physics of elementary particles and fundamental interactions. His principal areas of interest are the electroweak interactions, supersymmetric models, and theories with extra space-time dimensions. Though he is generally interested in all aspects of these theories, most of his research work is centered around predicting experimental signatures for such theories, especially in the context of high-energy colliding beam machines. He is also interested in the phenomenon of flavor mixing. His work, therefore, is a meeting place between theoretical ideas, experimental data, and numerical computation. Professor Srirup Raichoudhury has written more than 50 journal papers beside numerous web publications, conference presentations, invited lectures, and book chapters. He has written a book entitled Particle Physics of Brain Worlds and Extra Dimensions in 2016. Professor Raichaudhuri has a passion for history as a whole and history of science in particular. He has written about the less known chapters of Indian history and illustrated them with deep research pictures. He writes on popular science and the history of science for more than 12 years now, and his articles in this category are also published in different prestigious journals and volumes and widely appreciated. Professor Raichaudhuri loves teaching and is an excellent teacher, and we will realize that during the next hour when he talks on the life and work of Satyendranath Bose. Professor Raichaudhuri, please.
Thank you, Ornavo. Let me start by by sharing the screen, and let's see how that works out. Let me share my full screen. That's probably better. Share. Is it coming?
Not yet.
Not yet.
Not yet, not yet.
I had to click on it. Is it coming now?
Yeah, no, it's
Yes.
Yeah.
So let me make my presentation.
May I interrupt you?
Yes.
Would you be taking questions during your talk?
No, at the end, please.
Okay.
At
Thank
the
you.
end, please. At the end, please. But since Nananda has finished well before time, I think there will be plenty of time to take questions.
Okay.
And I can also speak at a leisurely pace. So I think we are not rushed for time.
Okay.
All right. So I'm ready. So should I start or no?
Yes, please.
Should I start?
Yes,
Yes. Okay. So I would like to first thank the West Bengal State University and in particular the Department of Physics, Dr. Shah for inviting me, my old and dear friend Ornavo Adhikari for contacting me to give this talk, and all of the other organizers for setting this up. I would also thank Nananda for his excellent presentation on the late Narendra, and also for agreeing to stay on to listen to this talk. So let's get down. So it's also, as a Bengali, it is a matter of, it's an honor and a matter of pride to be able to talk about the life and work of Satyendranath Bose, one of the great sons of Bengal. Now, before you start thinking that this talk is sponsored by Pepsi, which is why you will see that the sound thing in the middle, that's actually a simulation of a Bose-Einstein condensate. So before you start thinking that, let us see the man himself. So here is a picture of Satyendranath Bose as a young man and at the time when he did his famous work. But let me now take you back 100 years or more to the early part of the 20th century. And that has been described by George Gamow as 30 years that shook physics. So it's roughly the period from 1905, the miraculous year of Einstein, to about 1935, by which time, so relativity and quantum mechanics and then quantum field theory, these were the new ideas which came in at that time. Also, new areas were discovered, the nuclear physics, the fact that the quantum theory of solids, all of these were great discoveries, and they have been described as 30 years that shook physics. And indeed, we are still sort of the vibrations of that are still continuing. And here are the people who made it possible. So these are all familiar names and very famous names. I don't have to tell you, you can read for yourself, you're familiar with them. But you will see that there is one face among all of these which stands out, which is separate from the rest. And that is this one. The one face of a person, so you can see all the others are Europeans, white men, but there is one person who is definitely from a different part of the world and from a different culture, and therefore it is about, but the contribution is no less than the others. So we really have to be telling you the story of this person, Satyendranath Bose, Satyen Bose, as Bengalis love to call him. But this kind of a story should begin at the beginning. So again, let me take you back 100 years further. And I'll take you back to Europe at the beginning of the 19th century. And that flashing dot in the middle takes you to the beautiful town of Munich. And here you see here a nice picture, panoramic picture of Munich. That's the famous church of Munich. And here is the town hall. And here in 1814, a German optician called Joseph von Fraunhofer, he invented the spectroscope. Now, you are all probably familiar with the spectroscope. You have used it in the laboratory, done things, but Fraunhofer was the first to invent this spectroscope, and you see him here with a prism in his hand. And there is some friend who is looking through it. This is set it up at his house. Now, what are they looking at? They are looking at the sun. Of course, one should not look at the sun like that. We know that now. But anyway, in those days, people were more reckless. So imagine that is actually a photograph of the sun. You see a little sunspot at the end. And when you look at the sun through the spectroscope, what you see is this band of colors at the back. You know, the spectrum, this is the famous Newtonian spectrum from violet to red. And here in the middle of that, Fraunhofer, who looked at it in high resolution, found all these black lines. So lines of different widths, different spacing, different thicknesses. And these are known as the Fraunhofer lines. And this particular thing which you see is also known as the Fraunhofer spectrum. Now, over the years, people realized that if you look at the sun with a spectroscope during a solar eclipse, so what happens if you have seen a solar eclipse, total solar eclipse? You see that the sun gets covered by the moon, and you see a brightness which is due to the solar corona. And what happens then if the spectroscope suddenly gets reversed? All the dark lines become bright lines. The spectrum, of course, disappears, it becomes dark. So let's see that again. Let's, for example, focus on these two bright lines in the middle, in the yellow region. You see they become bright yellow lines. So this is the inverse Fraunhofer spectrum. Now this remained a mystery, nobody had any understanding. And things remained like that till about half a century later, the understanding came. So around the 1860s, and it was then that Robert Bunsen, now you are all familiar with the name of Bunsen, perhaps you have not seen this photograph. This was Robert Bunsen and his student, Gustav Kirchhoff. So Bunsen had invented this nice object, which you have probably all used in the laboratory, the Bunsen burner, and they used it to put different elements in the flame and see what kind of line spectrum it gives you. So they found that many of the line spectra, when you look at it in the position in the spectrum, they match with the Fraunhofer lines. And the real understanding came from Kirchhoff, who then proved from thermodynamics, beautiful proof, that the absorption and the emission spectra must be the same. What do I mean by that? He basically proved that if you have any substance, then the emissivity, which is the amount of energy emitted within wavelength around lambda, with lambda to some small range, at a particular temperature, the rate of emission of energy and the rate of absorption of energy in the same way is a constant. So if you have this, it's a constant for all bodies. So if you have some body which you imagine to be absorbing all, perfect absorber, to absorb all wavelengths, all kinds of frequency of light, then this absorptivity here will be unity. Okay, let's simply absorb everything. And then this object would be called a black body. So of course you don't need to write the one. So this ratio of this constant, this proportionality constant, which really depends on the temperature and on the wavelength. Otherwise it's a constant for all bodies. This is known as the black body spectrum. So the challenge was to find this function as a function of wavelength and temperature. And of course, one tried to do some experiments with this, but the best, and many people did, but the best experiments were done by these two gentlemen. I'm showing you a modern version of the spectrum, Ulmer and Pringsheim, working at Göttingen. And you see here that this is the nature of the spectrum. You are probably all familiar with the black body spectrum. This is the temperature in Kelvin. This is the spectral, the emissivity, if you like. And you see, this is the visible range. And as you see, that as you go to higher and higher temperatures, the overall emissivity increases, amount of emission, and also the spectrum moves towards the lower wavelengths. Of course, this is well known. However, a theoretical understanding was needed. So the first theoretical model for this was created by a gentleman called Wilhelm Wien. So Wien's, you have probably heard of Wien's displacement law. Wien also gave a formula to try to explain the spectrum. Unfortunately, this formula works well for small wavelengths and large frequencies. But as you go to large wavelengths and small frequencies, it breaks down. You see that this is the 7000 Kelvin line, and you would see that it changes. It just doesn't obey the law. Now, Wien's formula was prepared in a very ad hoc manner. So instead, what was done, a couple of English scientists tried to improve on it, and they gave a different formula. They were Lord Rayleigh and Sir James Jeans. So they produced a formula which had exactly opposite of Wien's formula. It worked well for large wavelengths, that is small frequencies, but as you went to lower and lower frequencies, it deviated. Not only did it deviate, but when you went to very low frequencies, the thing went up to infinity. Of course, that would mean an infinite amount of energy being emitted by the black body, which is not true. So this was known, and of course, this, you see, this is the ultraviolet end. So this is violet, and then if you go beyond violet on the ultraviolet side, then you have a catastrophe, a terrible thing happening. Infinite amount of energy being emitted when a finite image is emitted. So this, the formula of Rayleigh and Jeans broke down. Now the failure of the Rayleigh-Jeans formula, it gave a big jolt to classical physics at the turn of the 20th century. Now let me explain why that happened. Because, let's go back to Kirchhoff. So Kirchhoff, in proving his famous law, he had shown that if you have a cavity with insulating walls, and you have radiation, which is, let's say, a bit of radiation comes in here, then the radiation will keep getting reflected around the walls. And if this hole is very small, there's no chance of it coming out, or almost no chance of it coming out. So after some time, this has the same spectrum as a black body, because the radiation is essentially absorbed. This little spot is behaving like a black body. And therefore, whatever radiation will come out of this will also have the same behavior as a black body. Now you can study this using thermodynamics. And Boltzmann, you see a picture of Boltzmann here with his wild hair and beard. And he had proved the empirical discovery of Stefan. And what was that? That the radiation emitted by a black body per unit area is proportional to T to the 4. It's known as the Stefan-Boltzmann law. You see Stefan here. Now the point is that therefore the black body is obeying what it is, because this is well established by Stefan. Now what the Rayleigh-Jeans formula did was to simply take a cavity like this, to count the number of degrees of freedom and give all of them the same energy. Nothing could be simpler. So let's look at it again. So Rayleigh said that if the waves keep getting reflected back and forth inside a cavity, they will form a standing wave pattern. We are familiar with that. You've studied organ pipes even when you were in school. And the number of vibration modes of a standing wave inside a cavity between a frequency nu and a frequency nu plus a small change d nu comes to 4 pi nu squared by c cube, where c is the velocity of the radiation, which is the velocity of light. Because of course this is electromagnetic radiation. So this is the Rayleigh factor. Now Jeans pointed out that that's number of vibration modes should be multiplied by 2. Why? Because there are 2 transverse polarization modes of radiation. So when you add that to joules, you get the Rayleigh-Jeans factor. Now, okay, Boltzmann had told us that each mode of vibration or each mode gets an equal amount of energy, which is kt, and k is Boltzmann's constant. So therefore, by this law of equipartition of energy, multiply this by kt, and what you have is this formula: 8 pi k nu squared t by c cube. These are all constants, so it goes as nu squared and it goes as t. So when you go to large nu, small wavelengths, what will happen? This will keep on increasing. Moreover, this is the Rayleigh-Jeans formula. If you integrate this over with nu, you will get nu cubed, and then of course one of the limits is infinity. So therefore, you get an infinite amount of energy. That's the ultraviolet catastrophe. So nothing can be more simple and straightforward. But it's just wrong. It doesn't explain the behavior of the black body. So what's going on? So this is why I said classical physics received a big jolt at the turn of the between the 19th and 20th centuries. So what could have gone wrong? So what are the things which went into this calculation? Well, the counting of standing wave modes is simple, and nobody has any doubt about the wave nature of radiation. You see here, this is a diffraction pattern. Actually, this is from a laser, but even without a laser, with the spectroscope, you could see diffraction patterns, nothing new in that. Young's double slit experiment, all of you have probably done it in the lab. There's no question that Rayleigh's counting of standing waves was correct. Well, polarization of light is already well known. If you have a polarizing lens with your camera, turn it, hold it up, turn it around, you will see that light is indeed polarized. Look at a reflected light and turn it around, you'll see that falling. So there is no question that light is polarized. That's also not in doubt. So when you have a mystery, you call in a detective. So let us call in the greatest detective ever, and that's Sherlock Holmes. And he had this statement: it is an old maxim of mine that whenever you have excluded the impossible, whatever remains, however improbable, must be the truth. So what remains? The equipartition theory. That is the one which has got to be wrong. But how? Let's look at it a little more in detail. All right, so let's say that the energy which can go into any mode is arbitrary. So you have a classical theory. Energy is a continuum, so you have all these different modes, and you can put in any amount of energy into a particular mode. Now the probability for this, if you think, is given by the Boltzmann factor. So that was, applying the laws of probability, it will be simply the Boltzmann factor, which is minus exponential of minus E by kt. All right, so in that case, we can calculate the average energy. No problem with that. How do we calculate it? We take this probability factor multiplied by the energy, integrate over all energies, divide by the integral of the probability over all energies. All right, take any, plug in the factor, value of the factor. So E times exponential of minus E by kt and exponential E by kt, integrals of those. These integrals are simple to do, and they are done below. If you evaluate the top integral, you will get kt squared.
Srirup is not audible anymore. Is there any problem?
I can't even hear him. I think
Is there a
is
way of communicating this to Sirupda? Can you please, Orunauda, can you communicate this to Sirupda?
Yeah.
I think he should be communicated.
Yeah. I guess he's rejoining, so let us wait for him.
I was trying to call him. He's not picking it up.
So he has already left the meeting, so he will
Wait for
rejoin.
him then.
He has come back.
These are the sums. So this is the denominator, this is the numerator, and when if factors, you
The presentation is
share it afresh.
sorry.
Your screen is not visible. I mean,
we lost you for a few minutes.
So you have to start the screen sharing once again.
Okay, I see. Is it visible now?
Yes, it's coming. It's coming.
Yeah, it is. Make it full screen. Okay. No.
So, go back to the Boltzmann factor thing, that particular slide.
You were talking about the integral.
Yeah, this slide.
You were talking about the integral, both numerator and denominator KT factors. KT
With
square.
the Boltzmann factor, yeah. Yeah, this one, yeah.
KT square and KT, yeah.
This is the point at which I got cut off, is it?
That's right.
Yes.
Okay. But if you, so let me continue again from here. So if you look at this integral, well, this is simply the equipartition theorem, isn't it? This is the fact that the average energy is KT. So now if you go back, you multiply the total number of modes by this, and you will get the Rayleigh-Jeans formula. So what is wrong here? So everything looks correct. So the answer came from what was then thought to be a crazy idea by Max Planck. And he made what we will today call an inspired guess, but at that time perhaps it was more of a desperate guess. Okay, so let's see. So he said, what if the energy values, instead of being continuous, we took E, said that E can have any value. Suppose it's not that, but E can have only some discrete values. En, where n is an integer, so it is n times some fixed value E naught. Suppose we take this, what happens? Let's take the same formula for the average energy. So now these integrals will not be integrals anymore, but they will be sums over this value n. So let's replace it by sums. So En, where this is the Boltzmann factor with n, which is this, n times E naught by KT, and n E naught. And now you can go ahead and do these sums. So this is a geometric sum. It's an arithmetical geometric series. You know how to sum them from school. So let's sum them. And what do you get at the end of it? You get these fairly complicated factors, but when you simplify this, you end up with this form. You have the E naught in the numerator, and then you have e to the E minus, this Boltzmann factor minus 1 in the denominator. So this is clearly not KT. This is different from the Boltzmann factor. So, but why is it important? Let's see. It's a new kind of equipartition theorem, but let's see what the consequences are. Now let's look at small values of E naught. Physicists always take large and small values and take those limits to see what happens. And here you see that if you take small values of E naught, then you have a small factor here. So you expand the exponential as 1 plus E by KT, E naught by KT, and then what happens? The 1 cancels. I mean, there's an approximation here. And then you get back KT. So that means that the Rayleigh-Jeans formula corresponds to the small E naught limit of the Planck formula. So Planck concluded, going backwards, that the small E naught must be occurring where the Rayleigh-Jeans formula works. Where does it work? It works for large wavelengths or small frequencies. That's what we saw. So when frequency is small, then E naught is small. All right. So at least to a first approximation, then you take E naught proportional to frequency, which you can write as E naught is equal to some constant h, where h is n. Of course, this is the famous Planck's law, and this is Planck's constant. So let's go ahead with this. I mean, there could be corrections, but certainly when frequency is small enough, this law would work. So now into the same formula which I had before, instead of E naught, I have plugged h nu, and h nu by KT minus 1. So now let's go back to the Rayleigh number and the Jeans correction. So what will the black body spectrum be? First of all, this is the Rayleigh number, counting of standing waves in a cavity. Add the polarizations coming from genes. Now add the factor from Planck's summation, Planck's form, equipartition theorem. Put them all together and you get this formula where this is proportional to nu cubed rather than nu. And here you will get a exponential factor. This is known as Planck's distribution formula. Now the beauty of this is the following, that when nu is small, we've already seen the denominator will give you an h nu, so you'll get your nu squared and the t will come up, so you will get back the Rayleigh-Jeans formula. But when nu is large, what happens when nu is large? This factor becomes large here. So you can neglect the 1, so this becomes a negative exponential. And as you know, an exponential is stronger than any power, so then again the distribution falls. So it falls as nu squared for small values of nu, and it again falls in exponential for large values going through a peak in the center. And that is the qualitative behavior of the black body distribution, which was measured experimentally. So the Rayleigh-Jeans formula is matched and then it falls to 0, so that's exactly what. So it matches not only the qualitative but also the quantitative features of the observed black body spectrum. Because the beauty is that if you integrate this over frequencies, you will get a result which is proportional to t to the 4. That's also a beautiful result. Won't do it because it's technical, but you do get that. Moreover, so this figure you see is actually from the paper of Lummer and Pringsheim. That's why the writing is in German. Schwarzschild-Kuiper means black body. And what it shows you is that these dots are their experimental data, and these lines are the lines due to the Planck formula. And you see the agreement is simply too good to be true. Okay. I mean, I think if a student produces this kind of agreement in the lab, the teacher will be very suspicious of what you have done. But these were serious experiments, very carefully done. It was just too good to be a coincidence. But all of this depended on what? It depended on the energy values, instead of being continuous, being integral multiples of this energy packet. And therefore, one had to accept this. But this was sort of unbelievable. And what is the sense in talking of the energy of a wave? Remember, light, we started with light as a wave, or the thermal radiation being a wave, infrared radiation being a wave. And when you talk of the energy being tied up in packets, it simply has no meaning. So that's, yes.
May I interrupt you? Dr. Odhikari is saying that could you please kindly turn off that small bar at the bottom?
Turn off?
Yeah, there's a bar at the bottom. It says stop sharing or hide. Could you please click on the hide?
Oh, hide. Okay.
Yeah, okay. Thank you. Thank you. Please go
I've
on.
done that. I'm sorry. Yes. So you may have missed a few things at the bottom. It's okay. All right. So we are now asking. So the question which we asked was, what is the sense to talk about this? And this was a big puzzle. Well, Planck thought that he had an explanation. So he said, okay, we are looking at things coming from a cavity, okay? So therefore, the radiation is being absorbed and re-emitted from the walls of the cavity, okay? So let's blow up the cavity, and you imagine that there are some oscillators in the walls of the cavity. And it is these oscillators which are emitting the energy. So those oscillators, it's their property. They can only emit energy as packets. Now that's a possibility, right? Maybe the oscillator can hold only a particular amount of energy and it just emits that amount of energy. Okay, it's like, you fire a bullet. Whatever energy is in the bullet will come out, and then you have to fire a separate bullet. So the whole idea but then when they come out, when all of these different waves are re-emitted, then of course they merge together to give you waves. They merge and give you continuous standing wave patterns. So the analogy is like this. Imagine droplets of water coming from a tap, okay? So what happens, it's really individual droplets coming out, isn't it? You can see the droplets separately when the tap is turned down very low. But what happens if you turn it up more? These are still droplets, but they come out and merge into a continuous stream. So this was a beautiful explanation due to Planck that, okay, it's the oscillators in the walls which are responsible. So you have the wave nature, you also have this possible sum. And that's why you're getting the black body spectrum. Unfortunately for Planck, his own best friend, I don't have to tell you who he was, he killed the idea. What did this best friend say? Well, he gave a theory of the photoelectric effect, which you have all studied. And he showed, I'm not going to the theory of the photoelectric effect, you all studied it, that when light is absorbed and photoelectrons are emitted, it's all absorbed as a packet of frequency h nu, as Planck told us. And therefore, the energy goes partly to the kinetic energy and partly to overcoming the surface potential. Now, energy is therefore not just emitted from the walls of the container as packets, but it's also absorbed in packets. Well, if something is going to be both emitted and absorbed in packets, then it had better remain as packets. Okay. For example, suppose energy is going to be absorbed in packets, and just before it hits the metal, how is the radiation to know that it has to remain into packets? Okay. It will violate causality because it will be dependent on something is going to do in the future. So therefore, it had to remain in packets. And these are the packets, of course, we today know as photons. Now, an aside on this, Robert Millikan, you've heard of Millikan, Millikan-Zolthoff experiment, the famous experimental physicist from America. So he found this idea totally repulsive. He hated the idea. So he set up a beautiful experiment to prove Einstein's equation wrong. His purpose, and this is the experimental setup he had. Here was this photoelectric thing, and then he had the stopping potential and so on. You studied that effect. This is an actual apparatus. And he set up this experiment and took data to see what's going to happen. And this is actually from his paper. These are his results. And you see this perfect straight line of frequency versus the stopping potential or the kinetic energy of the electrons. And again, it's a wonderful straight line, an unbelievably good straight line. And this remains the textbook proof that Einstein was correct. So Millikan started by vehemently trying to prove Einstein wrong, and he ended up by vehemently proving Einstein correct. And so it was Einstein who had the last laugh, because his packets not only carry energy, but also carry momentum. And for his electron and all the carry momentum. Packets carry both energy . So again, somehow the photon has to know what the density of the electrons is before it interacts. So this is actually a causality violating thing. But it gave you Planck's law. And of course, instead of electrons, you could also have ions. And that was done by Einstein and Ehrenfest again in 1923. So there were many attempts made to get Planck's law by trying to understand the nature of the way photons are emitted or are absorbed by looking at the interactions of these photons with matter. The point is that all of them were wrong because all of these derivations assume classical statistics, and that is what they had not realized has to be changed. And the solution came from a quite different part of the world. We have to realize that all these developments which I've been talking about all have happened essentially in Germany and the neighboring areas. Okay, Ehrenfest was in Holland, but it was happening here. Maybe some things came from England, but it was not happening anywhere. And the solution came from far away from here, from Dhaka. And of course, in those days, you must remember exotic country. Maybe Europeans and Americans still think of it as like. But in those days, it was the land of elephants and maharajas and snake charmers. So the fact that the solution to the problem which none of them had been able to solve would come from here came as a huge surprise. And that, of course, is the work of S.N. Bose. So now it is time to switch over and let me tell you about the making of S.N. Bose. So now a little bit about his life. So this is the context in which his work was done. Now let's look at the life of Satyendra Bose. So again, instead of Munich, let me take you to Kolkata. Many of you probably are already in Kolkata. Okay, but I'm taking you to this part of Kolkata, North Calcutta. You go a little bit north of Muhammad Ali Park, close to, well, this, okay, this is that area. Let's look at a more detailed map. And this is the Scottish Church School. This is Bidhan Sharoni. Then we have the Goa Bagan Park. So this is actually the Goa Bagan area. Here, of course, is the famous Gobor Babu Akhra. All the heart of North Calcutta, very congested, as you can see from this Google picture. But I want to take you to this road. I don't know if it's readable here. This is called Ishwar Mill Lane. The Ishwar Mill has disappeared long back, but the Ishwar Mill name remains. And you see this house, and here, this is still well maintained. And this is the house in which Satyendra Bose was born at 22 Ishwar Mill Lane, Goa Bagan in Kolkata on the 1st of January, 1894. His father, Surendranath Bose, was an accountant in the East Indian Railways. So an accountant was a well-paid job in those days. And he was also a highly cultured man. So he knew a lot of things, including a lot of science. In fact, on the side, he had founded a small factory where he would manufacture chemicals. So the interest in science was already there in his house. And his mother, in the style of those times, she kept house, which was sort of normal in those days. And the only son, Satyendranath, was the eldest, and then there were 6 daughters. So he had 6 younger sisters to pamper him or to pamper if he wanted to. And of course, these cartoons are not their real things. Here is what they really look like. This is Suren Bose in his old age. You will later see that his son grew to look exactly like his father. And this is his mother, Amodini, and of course, in their old age. Now, the young Bose, you see a picture of him at the age of, I think, 11. He was educated till the age of 12 in local schools in that Goa Bagan area. And he was a bright student. He was especially strong in mathematics. But his father, of course, knew a lot of that mathematics anyway. So what he would do is that he would leave him a bunch of mathematical stuff, even before he started going to school. He would leave him a bunch of problems to solve before leaving for office. When he came home, he would find that the boy has solved them all, nicely and neatly solved them all. So this exercise in his early days, it whetted his appetite for more and more complicated problems. More complicated problems in mathematics, more in science, and that's basically how it came about. At the age of 12, he was admitted to the Hindu school. The Hindu school is really the nursery of the Bengal Renaissance. You see here a picture of the Hindu school, the beautiful neoclassical building which used to be the Hindu school in those days. Unfortunately, this building doesn't exist. What we have in its place is this. So, of course, more space, and I think not so good on aesthetics. Anyway, Satyendra Bose was always good at mathematics, and Hindu school had a legendary mathematics teacher in those days. In fact, even when I was in school, there was a legendary mathematics teacher there. So anyway, the teacher in his time was Upendranath Bakshi. So Upen Babu, I couldn't find a picture of him on the internet, so I just showed you a cartoon instead. Sometimes that happens. But it is related that once Mr. Bakshi, he gave the young Bose 110 out of 100 in his geometry exam. Not for solving the problem shown you on the right side, that is only to remind you how tough geometry problems could be. But in his exam, this young fellow had not just solved all the problems, but he had solved each of them in more than one way. So Upen Babu decided that this has to get 110 out of 100. And he was very proud of the boy. He said that one day, this young protege, this fellow, he will become a Laplace or a Cauchy from India. Well, Satyendra Bose did not become a Laplace or a Cauchy, but he became famous in his own way. And then came Presidency College. This again, in 1909, Bose entered the famous Presidency College. Of course, many of us have studied, Ananda, myself, Orunabho, many others have studied in Presidency College. Here is a picture from those days. This is the Presidency College. This is Head School. These two buildings are still as they are. This is the old Hindu school, which has now been demolished. This was the old Senate Hall of Calcutta University, also demolished. And now there is a multi-storied monstrosity in its place. And this, of course, is the College Square, the College Square Park. Again, it looks a little different nowadays. But anyway, Satyendra Bose entered Presidency College in 1909, and he entered the mathematics department. Of course, he loved mathematics, so he entered the mathematics department. And from there, in 1915, he did his BSc, and then from the university, he won his MSc in 1915 in mixed mathematics. So here is a picture of his mark sheet. And the mark sheet, you see the date 15/9/1915. And the marks you see are truly enviable. Let's look at them. 98, 85, 100, 89, 88, 94, 98, 84, 736 out of 800. Who would not like to get marks like that? If you are curious as to what he got 100 out of 100 in, surprisingly, it was not algebra or geometry or calculus, it was in physiology. Okay. And of course, not surprisingly, this won him the gold medal, and he stood first in his batch in this subject of mixed mathematics, which today we would call applied mathematics. Well, in 1914, while he was still studying for his MSc, Bose got married. Now, that was also fairly common in those days. His bride was called Ushabati Ghosh. She was the daughter of a prominent doctor. And you know what the traditions were in those days? That a rich man, like a doctor, like a flourishing doctor, he would find a bright boy as a husband for his daughter, and then this boy, as a part of the dowry, he would be sent abroad to study. And the expenses would be borne by the father-in-law. That was sort of a tradition which was followed in those days. However, Satyendra Bose refused to take the dowry, which was customary in those days, and he didn't let his father-in-law sponsor his higher studies. Instead, he said that I have 200 friends and all of them must be invited to the wedding feast. So, in fact, that is what happened. And this shows you part of his large-hearted nature, also his confidence and pride. And Ushabati, who was 11 years old at the time of her marriage, now, of course, this was also common in those days, she bore her husband 9 children, of whom 2 sons and 5 daughters survived into adulthood. 2 did not. Now, Mrs. Bose has been recorded by many people. She was a very gracious and uncomplaining hostess, because her husband had always diverse friends who were always dropping in. And it was very common for Satyendra Bose to say, "Ei je omuk kheye jabe." So she would have to provide dinners and lunches very at short notice. She was used to that. She was always a very gracious hostess. Just I'll show you a picture here of the same people in their old age. You see Satyendra Bose in the center, now looking very much as his father used to look in the old age. And this is his wife, also now grown old. And here are the children, grandchildren, big family. So he was always a very much a family man. Anyway, let's go back to his early days. So having passed his MSc with flying colors, as happens with many people, the young Satyendranath found himself in the great ranks of the unemployed. No job, no income. But he had a wife. And now, not only did he have a wife, he was soon about to become a father. So what did he do? He did what many people in the same situation do. He started earning a living by doing private tuitions. So he would go around on his cycle from one place to the other, teaching young boys. People didn't think of teaching girls at that time. Or anyway, it would be only done by women. So now he had one very famous student. Of course, that student didn't become famous for science. The student was Pramothesh Bulwar. So he was, of course, the young heir of the Gauripur state. He was a prince. And of course, he's much more famous for his acting skills. And I'm not sure how good a student he was. Maybe he wasn't. But Satyam Bose, one thing he could, was the good thing about it, was that because this was a royal family, Satyam Bose was paid a princely sum of 200 rupees per month. Now, I will show you some more figures from that time. The present equivalents, here they are. 250 crores and 170 crores. I mean, it's amazing. I wish we had such generous donors today for our universities and institutes. And in fact, even the government is not willing to donate this kind of money nowadays. But these people did. So, of course, it also tells you that they did not donate everything they had, so they had more money. So, therefore, that was the kind of money you could make by being a lawyer in those days. Well, with all this money and all this support, Sir Ashutosh built up a truly stellar physics department. And there were two professors, D.M. Bose, who was the Ghosh professor, starting from 1914, and C.V. Raman, later became the Nobel laureate, Palit professor from 1917, P.C. Mahalanobis, Prashanto Mahalanobis, who was still in Presidency College but would teach the Science College students, and then this bevy of bunch of young people, Meghnad Shah, Satyam Bose from the same class, Shishir Mitra and B.B. Rai, Bidhubhushan Rai, who were then also doing their PhD. They were all lecturers. You might be curious to know how much they were paid. So D.M. Bose got 600 per month. Palit professor had this high salary of 1,000 rupees per month. The lecturers were paid 125 rupees per month. Still far more than Ramanujam was paid in Madras. And what did they teach? So Mahalanobis basically taught mathematics. D.M. Bose, of course, he was not there from 1914 to 19, but when he came, he taught atomic physics. Quantum theory was taught by Meghnad Shah. Bose taught relativity. Mitra taught radio. B.B. Roy taught spectroscopy, and waves and optics were taught by Raman. Now, if you want to know more about this, I will do a little bit of an advertisement for my good friends, Gautam Gangopadhyay and Anirban Kundu. Anirban, I think you are there in the audience, or he was in the audience to begin with. They have just written this book called The Dazzling Dawn, and it describes this period of the Calcutta University. It certainly should be worth reading. I'm looking forward to reading it. It's just come out. All right, so these days went on like this, but in 1919 came the Jallianwala Bagh massacre. With that, it turned Indians who were still, sort of on the side of the British Raj, it turned them against the British Raj. You see a picture here of one of the great demonstrations which came out in the non-cooperation movement, so against the Jallianwala Bagh massacre. And in 1921, so Indians now came out in their millions to demand freedom. It was just, you also know that Rabindranath Tagore gave up his knighthood at that point for this purpose. So, of course, Bose was always sympathetic to the national cause. He had many friends among the nationalists, but he did not participate in the non-cooperation movement of 1921. And in fact, Sir Ashutosh, the Vice-Chancellor, he also did not approve of what he called disorderly agitation. But 80% of the students of Calcutta University responded enthusiastically to Gandhiji's calls. They boycotted their classes. At least generally students are always happy to boycott their classes. Though nowadays, after having been out of class for a year and a half, maybe people want to go back to their classes. But anyway, at that time, people publicly made bonfires of foreign goods. And the result of all of this was to make the government extremely angry with Calcutta University. So the government of Bengal, of course, British government of Bengal, threatened to withdraw financial support to the university unless there were 8 humiliating conditions. Conditions were called humiliating by Sir Ashutosh, which were met, and this would really give the Sarkari officials complete control of the university's internal matters. Sir Ashutosh fought this tooth and nail, but by 1924 he was dead. And in fact, his successor gave in to the government and accepted everything. So the government had a tight control over the university. If all of this sounds very contemporary, that's not my fault. That's the way things are. However, in 1921, when this tussle between Sir Ashutosh and the government was going on, among the jobs which were funded by the government was that of Satyam Bose. His lecturership was funded by the government. So that money would be withdrawn and he would be out of a job. And so at that time, he made his decision to move to the newly founded University of Dhaka. So you see here a picture of the beautiful Curzon Hall of Dhaka. This is the building, and one corner of this right wing is the physics department. So he went there as a reader. Remember, he was a lecturer in Calcutta University. So Dhaka University was being set up at that time. So Sir Philip Hartog, who was the new vice chancellor, he handpicked Bose and a few other bright sparks, including Ramesh Majumdar, J.C. Ghosh and others, and he persuaded them to move to Dhaka. What was the salary? It was a big jump. From 125 rupees a month, it was now 400 rupees, increment of 50 rupees per year, going all the way to 1200 rupees per month. This was an offer which Bose could not refuse. And so he decided to make the journey to Dhaka. So to do that, he took the train to the old Goalandu Ghat. From Goalandu Ghat, he took a steamer down the great Padma River, went to Narayanganj, took a train and ended up in Dhaka. However, setting up a new university is not easy, and my friends here who have set up WBSA will know that. Life as a pioneer is always hard. So Satyam Bose was writing to Meghla Shah, who always remained his lifelong friend, in 1921. He writes, "It has been well over a month since I moved to your part of the country. Work has not yet started. Your Dhaka college had quite a few things, because Meghla Shah was educated there in Dhaka college. But due to utter neglect, they are in a bad way. Perhaps I need not elaborate. On the table of the sahibs are scattered lots of nickel prisms, lens and eyepieces. It will require a lot of research to determine which one belongs to which apparatus. We do suffer from lack of journals and so on. Now they are talking about having a separate science library. So there wasn't even a good library at that time. So in these circumstances, Bose taught thermodynamics and electrodynamics. And at the same time, he had to set up laboratories, and he had to actually take the effort in buying books for the library. So his time was completely taken up. But within 2 years came another big jolt. Again, the Bengal government started interfering, and the Dhaka University faced a financial crunch. And they had to reduce the money. So among other economies which were forced, so Bose's nice appointment, regular appointment, 400 rupees a month, 50 rupees increment a month, and so on, it was changed to a one-year contract on a fixed salary with no promise of continuation. Now, that is really unfortunate. Of course, he was not going to give up without a fight. So actually, he wrote sharply to the Vice Chancellor, "I shall be in Dhaka after the vacation and shall stay on pending the decision of the Executive Council. But I'm afraid I can't give any undertaking to serve till 8th October. If the university authorities persist in their unjust decision, I shall have to seek for a job elsewhere." He was very clear that if you keep me on a contract like this, I will go.
I think we lost him once again.
I think so. I can't see him, hear him, or nothing is changing.
Yes.
I hope he will come back.
Yeah.
What about the Shubhajit? How is the YouTube streaming going?
Okay. So
Okay.
please, Sirudha is back. Yeah.
Was I off again?
Yeah, we lost you for
So
some time.
tell me where you lost.
So you start from the beginning of this present slide.
This one?
Yeah.
You saw this one, right?
No.
The present slide. I mean,
Vice Chancellor.
Yes. So Bose fought hard to keep his job. He wrote to the Vice Chancellor. I've read it already, so I won't read it again. He basically saying that, look, if you can't give me a guarantee to keep my job, I'll go and look for a job elsewhere. So the vice chancellor wrote back to him saying, no, but look, you're getting more money here than you could have got elsewhere, so just shut up. But he was also a fair-minded man. So he chaired this committee which resolved the following. So this is actually from that, this is copied from that letter. Mr. Bose to continue as leader till the end of the present salary session, and then to be granted 2 years study leave from the beginning of September 1924. And he was to get a total advance of 13,800 rupees from Dhaka University. And this is the money was enough to cover the passage to Europe, to and fro, and also a 2-year stay. In those days, the rupee was much more powerful, so he could have done it. But it was while this tussle was going on between him and the university that Bose wrote his famous paper on black body radiation. So that I will now come to, because this is the core of this talk. All right. Durga Puja of 1923. So Meghnad Shah would come home to his village every year for Durga Puja. And actually, since he came for the puja, he visited his friend Shotind Bose, and then the two had much to discuss. Okay, they're old friends, classmates. And of course, both being scientists, they would discuss a lot of science, among other things. And they were both teaching, so they also discussed their teaching, as we also do among ourselves. Now, Bose, who was teaching thermodynamics of black body radiation, which is basically the things I described at the beginning of this talk, he complained that the theory of Planck is very hard to teach to students because they keep asking awkward questions. I think that's an experience all of us face, that there are these awkward questions about Planck's theory. What is this? What are these oscillators and this and that? Now, Shah had recently moved to Allahabad University. Allahabad University had a much better equipped library. All these journals and things used to come there. So Shah had actually, he informed Bose about the papers of Pauli and of Einstein and Ehrenfest. These are the ones where they had assumed some kind of special interaction between the photons and, as I said, causality-violating interactions between the photons and the material. And of course, no Xerox in those days, so Shah had actually made notes by hand from those journals, and he showed Bose those notes. So a little bit of the physics here. So you imagine a sort of container. Look on the right, a container where there are randomly moving objects. So let's say that the red ones are photons and the blue ones are electrons. So of course there will be some amount of transfer of radiation. Now, the transfer, even as early as 1914, 1903, Lorentz and then Fokker, they had shown that the momentum transfer cannot take place through radiation pressure alone. Now, radiation pressure also exerts, is a way of transferring momentum. Okay, we know that. But they shown that it can't work. And Pauli showed that it could happen if you don't take radiation pressure, but if you take Compton scattering, which had just been discovered. But of course, he used this Einstein's 1917 derivation of black body spectrum. I showed you that with a nonlinear term. Okay, so A and B coefficients with this rho prime kind of nonlinear term. And then, of course, as I said, Einstein and Ehrenfest extended this to atoms. Replaced the electrons by atoms, but now Bose, of course, he looked at it, and then puja was over. Meghnad Shah went back to Allahabad. So Bose kept thinking about it, and now he decided to treat the photons purely as particles forming a gas, just like molecules of hydrogen, oxygen, etc. do. He said, we completely forget about the wave theory. Let's just treat them as particles and make them as a gas. Let's see what happens. Of course, the statistical behavior of a gas had been worked out by Maxwell and Boltzmann long ago. And here's another picture of Boltzmann when he was younger. And statistics. So how do we go about this? We say that if you write down the phase space of a gas, so what happens, you take the coordinates and you take the corresponding momenta, and there is a certain amount of uncertainty. See, imagine a phase cell, which is a small change in x, delta x, and a small change in p, and this little box would be called a phase cell. And imagine its volume is delta. So let's assume that the particle lives in such phase cells of volume delta. Okay, of course, in classical theory, everything is a continuum. So that delta is really zero, But let's just assume that it's delta for the moment. And it's a multidimensional space. So therefore, of course, it's not just x and px. The gases have 3 dimensions. So there's a y and a z and a pay and a pz. So it forms a 6-dimensional space, which I cannot draw, so I don't even attempt it, but you should be able to imagine it. So in this, there will be volume, not delta, but there's also the other dimension. So it will be volume delta cubed. So let us say the particle lives in a volume of delta cube, which it carries around with it. Now Boltzmann showed that the number of phase cells like this lying between the energy E and E plus delta E is given by this. So this is very simple. You take the Maxwellian distribution, convert it to energy, and what you have is this factor and root E, and then this is the volume, and you divide that by delta cubed. So that's the number of phase cells. Now, if you calculate the statistical probability of distributing these n particles, Ne particles, among these Ne configurations, so small n is the number of particles, capital Ne is the number of cells. If you distribute them randomly, so it's what are we doing? We are like you treat every particle like a colored ball, colored so you can distinguish them, and you imagine that there are a number of compartments of boxes. So each box corresponds to a value of E, and there are a number of compartments inside each of them which corresponds to N of E. So you want to distribute these colored balls among these compartments, and there are various ways of distributing it. Okay, depending on how you put the balls. If you do that, it's a simple problem in combinatorics to show that the number of configurations of these Ne balls among the Ne partitions is this factor, n to the Ne to the power small n, capital N to the small n by small n factorial. And when we take all the energy boxes into consideration, of course, this was only one box, right? One energy. When you multiply it over all the possible energies, then you get this factor. And this is just to fact that you could just redistribute the particles among the different boxes, or you could redistribute the different boxes among themselves. So that's the formula you would get. And n here is the total number of particles in all the boxes. So it is a sum over all these n's. Integral if you want to make it continuous. Okay, so we have, this is the total number of configurations. Now, the entropy of the system, we know how to find that. The law of Boltzmann tells us that it's log of this number of configurations times the Boltzmann constant. So that's what it is. So this is the total number of configurations, log of that, and you have the Boltzmann constant. And now the second law of thermodynamics tells us that when the gas is in equilibrium, the entropy must be a maximum. So therefore the distribution of particles, so what is the variable here? It is this distribution of particles, the small n, how the particles went into the different boxes and the different compartments of the different boxes. So this must be such as to maximize the entropy. Fine. But there's a constraint. One is the total energy must be fixed. That's which we call U, internal energy of the system, and the total number of particles must be fixed. So once we take these two constraints, you do a constraint maximum. Everyone knows how to do that using Lagrange multipliers, and that leads to the following distribution. So the Ne has some factors, it goes as root E and then E to the minus. This is your famous Boltzmann factor, which I've already used earlier. Notice something, there is no delta in this. The delta has cancelled when we found out the distribution. So now once it is cancelled, I can easily take delta to 0. So let me just go back a couple of slides. Where did I? Here. So the delta was here. So this delta is only a polite fiction. We use the delta to do our calculation, but now that it has cancelled from the result, we take it to 0. Now, this is something we are familiar with. We do box normalization, for example. Once something is cancelled, you take it to 0 or to infinity, it doesn't matter. For an ideal gas, if E is given by half mv squared, then the velocity distribution has this famous Maxwellian form. Gaussian distribution in the velocities. Okay, all this is classical physics. And this, in fact, this Maxwell distribution is going to look like this. It has this typical peaked nature. Now for photons, Bose was not working with classical particles, he was working with photons. So for this, he made 3 crucial physics assumptions. And these assumptions were much more far-reaching than even he imagined. But these are the ones which I would really, this is the real core, and this I would say is where his genius arose. What was the first distribution? The first of these assumptions. Instead of taking some imaginary fictitious delta, he took the phase cell to really have the area H. H is Planck's constant. But what does that mean? It means delta x into delta px is H. Have you seen this result? You've all seen this. This is Heisenberg's uncertainty principle 2 years before Heisenberg thought of it. This was 1923 and 24, I think. And then Heisenberg had not even thought in these lines then. Now, Bose had not thought as deeply as Heisenberg. He did not think in terms of measurement processes and so on, but he just took it. I suppose even if you asked him why he took it, he would say, I just took it to see what happens, but he did take it. So the first use of the uncertainty principle lies in the work of Bose, and he was actually very proud of it, as you will see later. The second of his crucial assumptions, he assumed that the photons are not just identical, but indistinguishable. Now, two particles which have a trajectory can always be distinguished. Even if they look identical, you can distinguish just by following what trajectory they followed. So the only case when when things are non-distinguishable is between waves, because waves superpose. And if 2 plus 3 superposes to give you 5, you don't know whether that is 2 plus 3 or 3 plus 2. So therefore, this assumption, which came later with the Du Bois wave-particle duality in 1924, this was also implicit in Bose's work. And what happened now is that the distribution with the boxes now becomes different. It's like you have the same kind of identical boxes, okay? You're not putting different colored, the balls are all colored the same. So obviously that if you can't distinguish, the number of configurations will also be less. And that calculation is simple. The combinatorial problem simply has to be done afresh, taking into account the fact that if you interchange balls in the boxes and partitions, give the same configuration. So earlier, for example, if these two were of different colors, if you interchange them, you got a different configuration. But now if you interchange them, what's the difference? It's the same. Now, this is not a new problem. This problem had been solved long ago. As early as the 2nd century BC, it's there in the work of Pingala. And then again by many scientists, from Omar Khayyam, Lilavati, Fibonacci, Cardinal, all the way to De Moivre. Very well-known problem in mathematics. And basically it arose from trying to understand if you take a word and if you want to use letters, and then if you use repeat the same letter, then of course that's not distinguishable, right? So if you have a double O, for example, then how do you know which is before and after? It will give you the same word. So that's basically where this competition came from. And okay, so now Bose certainly knew this because he had in his school days, as I told you, he was a brilliant student, and he had worked through this entire book, Algebra for the Use of Colleges and Schools, with numerous examples by I. Todd Hunter. I don't think younger people will have heard of this. It's a very famous book in the early 20th century, and some of the problems are unbelievably hard. I know because my mathematics teacher used to give me some problems from there, and I could never solve them. So anyway, Bose certainly solved all of them, and in fact, problem number 811 on page 536 of this book gives you exactly this thing. This problem, in fact, a more generalized version of this. So he knew the answer, and this is the answer. The number is not so simple as earlier. It has this problem. It has capital N plus small n minus 1 factorial by small n factorial into capital N minus 1 factorial. Okay, so that's the number of configurations. Go through the same process as before. Take all the boxes, all the energies. So this becomes the continued product of these. That's the Bose. This is now the Bose probability. This B is for Bose. And if these are photons in an enclosure, but remember that the photons in an enclosure are being absorbed and emitted all the time. So the total number is not fixed. So if you don't fix the total number, go ahead with this same thing. find the entropy using the famous law of Boltzmann. So log of that, and then this is the same thing. I've just repeated the same statement. The n, the small n, has to be such that it maximizes this quantity rather than the earlier one. What had I said earlier? Subject to fixed total number and fixed total energy. But now the fixed total number is gone for photons. Only fixed total energy. So do the same exercise. When you do it, you get the following distribution. N is proportional to the total number of states, and lo and behold, you have the Planck form. You have the Planckian form in the denominator. What has been used here? Nothing but statistics. Okay, no interactions between the photons and the walls or anybody. It's just the photons themselves, how they are distributed, only because you cannot distinguish between one photon and the other. That's all. Now, of course, you also need to calculate this NE. Okay, where did Planck take it from? Planck took it from the Rayleigh formula, Rayleigh-Jeans formula. Their way of calculating it. Standing waves in a cavity. But Bose did not have standing waves. He had only particles. He had a gas. So his calculation of this was also novel and far-sighted. How did he do it? For photons, he went ahead and he combined Planck's law and Einstein's mass-energy relation to write this. So photons are massless, so energy is Pc and h nu. And now here, you replace nu by c by lambda and you arrive at P Ec is equal to hc by lambda. So the c cancels and you get P is equal to h. Now this is de Broglie's relation. The de Broglie relation, which was arrived, but Bose had already used it. It's amazing. He had already used it without all that fanfare about wave nature and so on. So taking momentum to be this, the number of phase cells lying between momentum this and this must be given by this quantity, where V is the volume of the cavity. And now you replace the P by h nu by c and you arrive at this. Take it per unit volume. What do you get? This is the Rayleigh factor. No stationary states, only phase space. Okay. And when you plug this into the statistical distribution, now you know what you will get. You got this result, which is identical with the average energy multiplied by h nu. And you get this form. Everything is there in Planck's formula except a factor of 2. Okay, Planck's formula has 8 here. He got a factor of 4 here. Now he was short by a factor of 2. And it is perhaps his most amazing insight, and the one which is least known, is how he found the factor of 2. Remember, he didn't have polarization. The third assumption, he says, is that the photons have 2 possible angular momentum states. Either they spin around their axis, either they go clockwise or anti-clockwise. So this is the concept, and so therefore that's what he gave him as factor of 2. Now this is the concept of spin, intrinsic spin of the photon, 1 year before Uhlenbeck and Gauss-Schmidt proposed it in 1924. So again, before quantum. And you'll see later why this didn't get the credit it should have, but this was also there. So 3 basic and very famous assumptions were all sitting inside the Bose derivation. Actually, Bose did not realize how far-reaching these assumptions were, but he did realize that he had done an important piece of work. He had arrived at the Planck formula without any interaction, assuming any interactions, just by distributions and assuming that things are indistinguishable rather than distinguishable. So he wrote it up in a very modestly titled paper. Instead of saying, I have revolutionized the subject of quantum statistics or invented the subject of quantum statistics, he wrote Planck's law and the light quantum hypothesis. Well, this is not the manuscript of the paper, that is lost. This is the same thing written up by Bose later for Einstein, and it's been found in the Einstein archives. So I wanted to show you his own handwriting. But anyway, full of confidence, towards the end of 1923, Bose sent his manuscript for publication to the British Journal. This was then the physical review letters of the time. It is called the Philosophical Magazine. After 6 months, the journal sat on his thing for 6 months. After 6 months, they sent back his manuscript with a curt note saying, sorry, we can't publish it. The referee has said this is not worth publishing. That's it. So all those who are listening to me who are regularly published papers will be able to empathize with this. Often referees are not able to understand or appreciate your work, and we are all familiar with this. And of course we do our own refereeing, so perhaps we make these mistakes also. But the note said that but in those days no explanations were given, so the referee report was not yet closed. The editor simply said we can't publish it. Now Bose was getting a bit desperate. So in June 1924, and his job was only till September, so now he took a bold step. He sent his manuscript to Einstein. So Einstein then was around 43, 44. He was in the height of his name and fame. In 1921, he had won the Nobel Prize. In 1919, general relativity had been proved correct. He was also the editor of a journal called the Zeitschrift für Physik. And he was a little unlike most editors because he did a lot of the refereeing himself. Because perhaps his experiences in the patent office had made him curious to know what kind of ideas people have. So a lot of papers which had been rejected for many people were sent to Einstein, and he actually read them and recognized their worth. And that certainly included Bose's paper. So let me show you what Bose wrote. This is a facsimile of his own handwriting. He said, "Respected sir, I have ventured to send you the accompanying article for your perusal and so on. You will see, he says, I have tried to deduce the coefficient 8 pi nu squared by, this is the Rayleigh-Jeans factor in Planck's law, independent of the classical electrodynamics." So he's very proud of it. Okay, this is what he thinks is his most important piece of work, not the statistical part. And then he goes ahead and says, if you can publish in Zeitschrift für Physik, and he says, I do not know sufficient German to translate the paper. But then he says that you may remember, I do not know whether you still remember, someone from Calcutta asked your permission to translate your papers on relativity in English. So this is clearly not quite honest, because he's saying that it's clear, and in fact this is the paper, this is the book he published. He and Saha together, they translated the papers of Einstein and Minkowski on relativity into English. So if you can translate English into German, perhaps you can translate German into English, you can perhaps translate English into German also. Anyway, Einstein agreed to translate it, but he also knew that Bose knew enough German to, right? So he wrote back to him in German. The letter by Einstein is in German, and you see here that it's dated 1924, 2nd July 1924. And what does it say? This is what it says in English. So this is the paper which got published, and I'll come back to this in a moment. So he says, dear colleague, I have translated your work and communicated it and so on. So he likes it. So what he says, it signifies an important step forward, and I liked it very much. You are the first to derive the factor quantum theoretically. And then he says, because of the polarization factor too, not wholly rigorously. Note that Bose has not said polarization. Okay. He did not say polarization, he said spin. But anyway, Einstein got, it's a beautiful step forward, very friendly greeting, very strong praise from the great Einstein. Einstein was not quite sure what Bose's name was. So he said, Fon means by. So by Bose. He thought his name was only Bose, and then whatever. But what is important here is that he added a note of support at the end. You know, this is something few referees are willing to do. He says, in my opinion, Bose's derivation signifies an important advance. The method used here gives the quantum theory an ideal gas, as I will work out elsewhere. Now, this is something we don't do nowadays. He neither invited Bose to collaborate on taking the work ahead, nor did he ask Bose to visit him at Berlin, though he could easily have. Instead, it is that, okay, this is good work, but now I will take it ahead, not Bose. Not only that, when he translated Bose's manuscript, he used the word polarization, you see here. So you factor of 2, you see, with 2 zoom multiplication, so the factor of 2 multiplicative factor is due to polarization. Now, what is polarization of, so Einstein, he changed Bose's angular momentum states to polarization. Then he himself says, because you have polarization, it's not rigorous. So that it's very strange. It shows you that even great minds are not always correct. the early days. Anyway, at least Bose's idea had won some recognition. In fact, the only one who afterwards stood up for his spin idea was C.V. Raman. In a paper with Bhagavantam, he had written various things. So he had said that, we understand from personal communication that he envisaged the possibility of the quantum, whatever, also spin. Anyway, it didn't get much traction. But Einstein's postcard, this is what an Indian passport used to look like in those days. Einstein's postcard did serve to smooth the path to getting visas for Bose's Europe trip. And in fact, for the German visa, on Einstein's letter, the fee was waived. It's sad that the same Einstein had to leave Germany later. Anyway, so in September 1924, Choten set sail for Europe. In fact, he was the last of his illustrious classmates and colleagues to do so. So Meghnad Shah, Shishir Mitra, Bibi Roy, all others had gone to Europe before him. And why couldn't Choten go? There's a little story in that. There used to be, there is, in fact still is, there used to be a scholarship called the Premchand Roychand Scholarship, which was used by Meghnad Shah and others to go to Europe. Now the Premchand Roychand Scholarship had a condition that it was to be given to somebody who was not married. Choten was married immediately after leaving college or university, so he was not eligible for this. He had to wait till Dhaka University sponsored his trip. Anyway, finally he did reach Europe, and on November 18th, 1924, he reached Paris. Why did he go to Paris? Why not straight to Einstein? Because in 1923, one R.L. Day from Dhaka University had been sent to work with Madame Curie at her laboratory in the Radium Institute at Paris. So while Bose was traveling, his mails were being sent on to Day, and he needed to pick them all up from there. So, but in Paris, what he found is there was some cheap accommodation. There was an Indian Students Association which had lodging at 17 Rue des Sommeras, and there he found some of his old friends, who were revolutionaries. So they were in France, so out of reach of the British. So he found old friends there and so on. So he wanted to stay there sometime. So he was advised that if he wanted to work in Madame Curie's laboratory, then he should first meet with Paul Langevin, who was well known to be Pierre Curie's student and very close to Madame Curie. So now when he met Langevin had already read Bose's paper as translated by Einstein, and he had been very impressed. So in fact, he welcomed the young Indian with open arms. In fact, from then onwards, for many years, he was a very good friend and mentor for Choten. So he learned that Bose was interested in both crystallography and in radioactivity. He gave him letters of introduction to Madame Curie and also to the crystallographer Maurice de Broglie. So Maurice de Broglie was the elder brother of the famous Louis de Broglie of wave particle duality. And so Bose went to meet the great lady. Can you see this video? This is a contemporary of Madame Curie. You already see her looking rather ill from radiation sickness, but that was not known at the time. So now Bose, the lady, famous lady, greeted Bose warmly. She said, since you are coming from Langevin, I will certainly allow you to work in your Radium Institute. But, so she spoke very good English herself. She told Bose, you have to wait till the new year. Until then you learn French. Since your predecessor, Dr. Day, he did not know how to speak French. So he had a lot of difficulty in communicating with people. So why didn't you wait? So this was in October. So he said, now you wait, you learn French for 3 months. And then in January you come. So Bose said, okay, madam. He was so awestruck that he forgot to tell her that he had learned French 10 years before. He could read, write, and speak French fluently. But he didn't dare to contradict her. So much was he in awe of Madame Curie, or that was the kind of personality she had. Anyway, so he reconciled himself to work for the time being in the X-ray laboratory of Maurice de Broglie. And that's his picture here. And of course, there he was happy talking French with the others. In fact, he was happy. The days slipped into weeks. Weeks went into months. He remained in Paris working in the Broglie lab. And then from the new year 1925 at the Radium Institute, he reveled in the atmosphere. He learned cutting-edge techniques from the experts. he was discussing theory with Langevin and with Louis de Broglie, and enjoying the company of the revolutionaries, Indian students, and so on. So he was a man who made friends easily. For example, this young doctor, Bertrand Zadoka, he was a very good friend, lifelong friend of Bose. He had a pretty young sister who was then a student, Jacqueline. They were his friends. They later came to visit him in Calcutta and so on. But meanwhile, he had written a second paper, and that had been published again by Einstein. And Bose had considered an ideal gas. Now here he had considered ideal gas instead with radiation. So now there were two things, not just the gas, but not just radiation, but radiation and ideal gas together. That's the kind of picture I showed you earlier. And he found that if he just does statistics, no interactions involved, the gas molecules will have a Maxwellian distribution and the photons will have a Planckian distribution. Why? Because the gas molecules are distinguishable, the photons are not. And this was translated by Einstein, and this time he got his name right, by S.N. Bose. And if you're wondering what this is, Romna is the place in Dhaka where the university is located. Okay, now this time he got the place wrong. He should have written Dhaka. Instead, he wrote Romna. But anyway, the point is that I've shown you, it's only distinction what needed. So no interactions of this kind. But Einstein wasn't giving up so easily. Meanwhile, Bose had written to Einstein saying, I have been granted leave and I have arrived in, I don't know if it will be possible to work with you. And then Einstein replies politely, thank you sincerely, I'm glad that I shall have opportunity. So please do come. But he still, I'm not in agreement with your basic principle. Basically, he still thinks that the distributions come about because of interactions between the matter, and not because of the statistical behavior. But while he is contradicting Bose and protecting his own idea, he himself was feverishly working on Bose's idea. So in 1924, he had worked on the statistical distribution of the atoms in a monatomic ideal gas, what we would now call a massive boson gas. And then in 1925, he showed that the molecules in this tend to cluster in the ground state, which we now know as Bose-Einstein condensation. So he was not sharing this work with Bose. And in all his papers, of course, he scrupulously acknowledged that the statistical method had been discovered by Bose, but he was not going to share the glory of these things with some guy whom he had never met from some faraway Asia. No. It was Paul Dirac who made Bose immortal. In 1926, he coined the expression Bose-Einstein statistics and Fermi-Dirac statistics. And in fact, very modestly, he named the particles which obey Fermi-Dirac statistics as fermions. So if these had to be fermions, the other one had to be bosons. And that's the name. So it was not, the credit really comes from Dirac and not from Einstein. But Bose was never bothered about Einstein's selfishness. To him, Einstein was the master. Einstein was God. And so after 1 year in Paris, he was able to move to Berlin in October and meet his hero. So Einstein was then director of the Kaiser Wilhelm Institute for Physics. So today is the Max Planck Institute, I think, for radiation chemistry. But the building is the same. Fortunately, it survived the war. And then this is where he was able to meet the great man. So a little video clip of Einstein. Rather tired in the evening, I guess. Maybe you're also equally tired, but I'm almost near the end. So through Einstein, Bose came to know the whole Berlin gang, very famous people, Max Planck, Nernst, Hahn, Meitner, von Karman, Schillert, Wigner, De Bayer, Hermann Mach, Fritz Haber. But they all revolved around this one famous person. So he was the center of attraction, center of everything. And then in 1925 came the new quantum mechanics. 3 famous papers, first one by Heisenberg, then by Born and Jordan, and then by Heisenberg, Born and Jordan together. So there's a lot of excitement which came as a result of this. So Bose was writing to this young Jacqueline, who was still in school at that time. So he says, everybody seems to be quite excited in Berlin the way things have been on with physics. First, on the 28th, Heisenberg spoke in the colloquium about his theory. Everybody is quite bewildered. There's going to be very soon a discussion of Schrödinger's paper. Einstein seems quite excited about it. The other day, coming from the colloquium, we found him jumping in the same compartment where we were, the train, and forthwith he began to talk excitedly about the things we have just heard. We were all silent, but he talked almost all the time. unconscious of the interest and wonder that he is exciting in the mind of the passenger. So the other people were probably wondering why this guy is jumping up and down. What's it all about? So Einstein, in fact, suggested to Bose that, look, there is this new mechanics, and why don't we collaborate on two problems? First of all, whether there are new statistics, whether this one which you have discovered, does it imply some subtle interactions among the photons themselves? It does not. It does not come from interaction. This was simply wrong, so therefore this problem will go nowhere. We do know that photons do interact among themselves very weakly, but that only comes when you have high densities like a laser or something. The second question is, how could these transition probabilities of spontaneous and stimulated emission of radiation, see, he's still thinking in terms of his own work, be derived in the new quantum mechanics? Now we can do that. Okay, but there, to do that, you have to do a perturbative calculation in the dipole approximation, which required much more development of quantum mechanics than was possible at the time. So not surprisingly, Bose did not make any headway out of these problems. He just couldn't get anywhere. Instead, he started working in Hermann Mach's crystallography lab, continuing the work he had been doing with Maurice Debreu. So basically, with Einstein, he had many discussions. He visited him regularly, he had all manner of discussions, but these problems remained unfinished. The first one, of course, there is no solution. The second one was solved much later by other people. By mid-1926, his term was over, he came back to India. Working with Einstein was not easy. A close friend of Bose has described how many years later he opened up a little about his experiences with the great man. So he writes, one day he was reminiscing about his Berlin days. Einstein had given a problem to solve. Shotin Babu told me, I thought about it for 3 days, and then I went to see him with my solution. Well, Einstein looked at it and said, well, this is not wrong, but not the way I wanted. This clue does not open up any new possibilities. And then look at what he says. Please don't waste my time with such trifles. So it's very rude. And I don't know. So the truth is that Einstein didn't like being proved wrong any more than anyone else. As a matter of fact, he was now 46 years old, and his intense creative period was more or less over. The best work he was, in fact, these are the last important works he was to do, were on Bose statistics. After that, he went on to his unified field theory, which, as we know, is a dead end and it didn't lead anywhere. Perhaps the result of this interaction was that Bose did not venture into theoretical physics till 1939. So that was full 16 years. 13 years after that. So the last part of my talk is Bose as the sage. So I will now, it's been a very long talk, so I will now just quickly go through the milestones in his life. In 1926, he returned to Dhaka as a hero. He had reference, he still didn't have a PhD, but he had reference letters from Einstein, Lajova, and Hermann Mach. So they immediately made him professor and head of the Department of Physics at Dhaka University. After 1 year, he became Dean of Science. And as such, it was his job now to set up laboratories in chemistry, optics, and crystallography. And he started publishing in these areas, not in quantum mechanics. In 1938, he was offered the Palit Professorship in Physics, but by then he had come to love Dhaka, so he didn't take it. It was taken by his friend Meghnad Shah. Well, I have a picture here of the head of department's room at Dhaka University. And I'm very proud with this picture, because not only is it with a very, very famous physicist of today, that is Professor Ashok Sen, and this is Professor Arshad Momen of Dhaka University, but also right at the back there is this board, I'll enlarge it for you, showing that Professor Bose occupied that chair, empty chair there, from 1926 to 1945. And what are the kind of papers he wrote there? I'm just taking you through. So you see, here is a paper on electrochemistry. Here is a paper on atomic physics, spectroscopy. 2 papers on statistics. This D2 statistic was invented by Mahalanobis, and he was applying that, he was doing mathematics with that. Anomalous dialectic, so the work done on the atmospheric physics and radio physics, essentially what would be called today. Then he comes back, studies in the Lorentz group. He comes back to theoretical physics, mathematics. Complete solution of this is the Klein-Gordon equation, inhomogeneous Klein-Gordon equation, and he comes back to it as late as 1940. Reactions of sulfonizides with pyridines. So chemistry chemistry. And Dirac equations and the Zeeman effect, integral equation associated with the equation for the hydrogen atom. So it took him many years, but then he did come back to some quantum mechanics afterwards. Anyway, in 1945, he left Dhaka forever. So he was offered the Khaira professorship at Calcutta University. And by then, Hindu-Muslim riots, and it was insecure. So he finally, I think very regretfully, left Dhaka. He was never able to go back. And they have preserved his chair and his table and his office exactly as it was. I've seen it. This photograph is taken by myself. That is the chair where he used to sit. In 1947 came independence, second partition of Bengal, people scrambling to reach safety. These images have become very familiar even nowadays. And then, but while others became institution builders, Bose remained content to remain the quintessential scientist. So his other contemporaries, Mahalana Base, Raman, Bhabha, Sarabhai, Meghnad Saha, J.C. Ghosh, they all made institutions. Bose never built an institution. He just stayed with science. He was different. He was indeed nominated as a member of the Rajya Sabha, but he did accept it, but he only gave 3 speeches. Let's not forget about them. He retired from Calcutta University at the age of 62, and he was appointed Vice Chancellor of Vishwabharati in 1956. Well, as we all know, even from nowadays, that post is always controversial. So Bose lasted there only 2 years. After 2 years, he got fed up and resigned. Then he was elected a Fellow of the Royal Society very late, in 1958. It was only because Dirac had come to Calcutta in 1957. He was aghast to know that S.N. Bose was not an FRS, so he went back and had him nominated. Bose became a national professor in 1959. This post was renewed every 5 years till he died. Calcutta University made him an emeritus professor and gave him labs, but now he was 65 years old, so he continued to train students in experimental techniques. The Bongyo Vigyan Parishad had been founded with Bose as its president, and he always, throughout his life, he advocated teaching of science through the mother tongue, and he was appointed president of the Indian Statistical Institute at age 73. And then in 1974, it was Bose's 80th year, as well as the 50th year of the discovery of Bose statistics. So year-long celebrations were held in Kolkata and elsewhere, a long round of seminars, symposium, felicitations, and cultural programs. And Bose himself participated in these with his customary enthusiasm. He was always an enthusiastic man. He was so happy. He said, "Now I feel I do not need to live any longer." He felt vindicated. I'll show you a little clip of Bose at one of these functions. He's very old, as you can see here now. Walking with a stick. Unfortunately, he had his wish. The excessive strain told on his health. He was just 80 years old. And 1 month after his 80th birthday, he passed away quietly at his Kolkata home. Not since the death of Rabindranath Tagore had there been such an outpouring of public grief in 1974. Well, I was a little too young to remember the details, but I remember the newspapers carried accounts of it for 2-3 days and a lot of information. Then perhaps Naranda will remember a little more, but not since the death of Tagore had people really felt such a sense of loss. So, well, the body of Bose was consumed by the flames, but the statistics he discovered lives on. Even the light which comes from the flames, the photons which are carrying my words and my slides to you, all of this obeys the Bose statistics, quantum statistics. So before I finish, let me just say that we need to understand Bose. I mean, there are a lot of things said about Bose, both good and bad. But we need to understand that he was a complete product of the Bengal Renaissance. He was a mathematician, physicist, chemist, spectroscopist. He was a good musician. He was a very wonderful conversationalist. He did some work, and he was a good administrator too. Maybe not in Vishwabharati, but in Dhaka University, he was an administrator for more than 20 years. He was a man of letters. He wrote very well. He loved food. He was a family man par excellence. And everybody said, who met him, said that he was full of what's called the milk of human kindliness. He was a nice person. He was a nice and a loving and a very lovable person. the 1923-24 work done by him, this bridges the gap between old quantum theory and quantum mechanics. See, he had not formulated quantum mechanics, but he could use the results. He could sort of, to quote Shakespeare, he could see quantum mechanics as through a glass darkly. He had an inkling of what the results were. He did not know exactly why they were there, but it's amazing intuition which led him to those results. But when actual quantum mechanics came, well, he didn't like it because he didn't work on it till it was very well established, beyond doubt. But his great work was not achieved, as some foreign writers have tried to say, by serendipity, which basically means by guesswork, but by deep reflection and some absolutely amazing physical intuition. I think that is what people find difficult to believe, that so much physical intuition could be had by somebody from a remote part of the world. So that's where it stands. So one of Bose's students in the final years, he wrote, one should not expect people like him, that is Bose, to be doing routine work in one particular line. That would be insulting him. They are after the final truth, not caring for what can be achieved on the way. Everything is eternal. He was an aristocrat. And that is, I think, the way to understand Bose. He was undeniably the founder of quantum statistics and therefore a pioneer of a great deal of modern science. And that is what we should remember. After all, and many people ask that, what did he do after that? Why should we ask this question? This is enough to put him in the ranks of all the immortals. After all, do you ask what Dalton did after formulating his atomic theory? What did Neil Armstrong do after visiting the moon? What else did Tulsidas write after the Ramcharitmanas? Nobody asked these questions. These people are remembered for these fantastic achievements. Satyam Bose should be remembered for the same. And so I will conclude my talk with this only one and only color photograph of Satyam Bose available, playing his favorite Esraj, and with his famous formula here, which was discovered by him, understood by him. So on this note, I'll conclude. I think it's a very long talk, so I'll conclude it now. So thank you all for your patience and for listening. So we conclude with...
Thank you so much, Professor Rai Chaudhary. It was as if I had gone back to my 1990 class in Science College. Very comprehensive talk, lucidly bringing out the life and work of this great man we take great pride in.
Maybe I should stop sharing now, or maybe I'll keep it up.
Yeah, please do.
Yes.
Please do. Can we take, Sudha, can we take a few questions?
Yes.
If there are. Dr. Shah? Anirban?
I don't see many questions in the YouTube chat.
Okay. So we would like to hear from Naranda and the other seniors. Any anecdote, anything you want to add on to Professor Rai Chaudhary's talk today? Those who have any kind of memories of Professor Bose or his students, anything that you would like to share? Do we have Naranda with us?
But Luke's talk was so exhaustive that hardly anything can be added. But I can add one anecdote which we heard from our teacher in Presidency College, Professor Shamul Sengupta. So Shamul Babu once said that, so he was in Dhaka at that time.
Naranda, a bit louder, please.
Sorry. So this we heard from our teacher Shamul Sengupta, Professor Shamul Sengupta in Presidency College. Am I audible now?
Yes.
So this is an anecdote. When Professor Satyam Bose was in Dhaka, so some chemists were doing an experiment. So they're repeating some experiment done in Germany. So the idea was after adding something in the test tube, they were pouring water, and according to the experiments reported by the German group, there should be a precipitate, but they did not observe any precipitation. So after a few trials, they went to S.N. Bose for his advice or opinion about that. Satyam Bose thought for a while and then said in Bangla দেখ ওরা কি আর বুড়ি গঙ্গার জল দিয়েছে, ওরা তো লাইনের জল দিয়েছে। তোরা বরং জলের বদলে বরফ দিয়ে দেখ। They added ice and immediately they got the precipitation. So it was all about temperature.
Temperature.
Right.
Yes.
So this was the anecdote that we heard from Professor Sengupta.
Well, Shoten Bosch,
It was a great talk, in fact. It was a bit big, but worth it, because it is quite exhaustive.
well, I'm glad you said exhaustive and not exhausting. I was afraid of that because it was very long. But I thought I should tell you the whole story.
Yeah. It was great, in fact. Yeah.
Thank you, Naranda.
Hi,
Thank you so much.
Thiru.
Ashita? Yeah, Ashita has a question.
Thiru, it was a great talk, very, very enjoyable.
Thank you.
I'd like to share one thing that most people probably wouldn't know. And this comes from the field of music. And Shoten Bosch's involvement in it, in actually musicology. Okay, all of you know or may have heard about Reba Muhuri, who sang in Shatranj Ke Khiladi and Jai Baba Pelunath
Yes.
and Sonar Kella. Reba Muhuri's father was Omyonath Shannal. Okay, he was a quite great musician, but usually people don't know about him that much. And so he did a statistical study on Indian ragas and raginis based on certain things, which I cannot go into detail here. And S.N. Bose was Omyonath Shannal's friend. And so S.N. Bose was deeply involved also in that study and helped Omyo Shannal in that. Okay, and it actually resulted in beautiful things which are, as followers of Indian classical music would know about Bhat Khandeji's theory of male paddhati or thought system and so on and so forth. These are actually quite opposite, because this thought system doesn't really work, or it's not really a theory. It's a sort of a classification of ragas, you may say. But this S.N. Bose and Omyo Shannal, it's mainly Omyo Shannal's work, but S.N. Bose was helping him in that analysis. And so based on this, actually in 1959, Omyo Shannal published a part of his work called Ragas and Raginis, published by Orient Longmans, and in the introduction part, he acknowledged Shoten Bosch there. So this I wanted to share.
Thank you so much, Ashita, for the beautiful rebellion. Yeah.
Sorry, Ashita,
Yeah.
do a favor. In the chat box, can you please write the reference that you were talking about, the publication?
This book is long out of print, but I have a
Oh,
PDF. I have a
Oh,
PDF, and you can just search Omyonath Shannal, Ragas and Raginis.
Oh, thank you.
I'm sure Google will give you a PDF copy.
Okay, thank you very much.
Yeah.
Okay, Sriruddha, there's a question that is there an exclusive book exclusively on Professor Bose, on
There
his
is-
life and work? Yeah.
There is a book on his life and work which was brought out in his centenary year, which was 1994. It was brought out by the S.N. Bose Center. So that book it's available on the internet. If you search for it, you will be able to find it. The entire PDF form is available on the internet.
Okay. Thank you. So, Bonnie, that answers your question. So, okay. So, quick question. Yeah, Anirban?
Arunabada had a question because he had raised hand.
Arunabada has.
I didn't have any question.
That has been answered.
That is
Okay, I
taken care of.
have one comment in the YouTube.
Yes.
Bikash Sarkar, he says, can you please elaborate a little on the basic difference between the approaches of Planck, Einstein, and Bose? I think he is talking in connection with quantum theory.
On the approaches of Planck, Einstein, and Bose. Well, I think I have elaborated a lot on that, but let me say a little more. See, Planck was the pioneer. I mean, he introduced this discreteness of energy states himself, found the right distribution for black body radiation, but he himself was very uncomfortable with it. He was uncomfortable because, and so therefore, he tried to explain it within the framework of classical physics. Now Einstein took it ahead. Einstein was indeed, with the photoelectric effect and the combination of that, he really established the existence of the quantum of energy. So, but he himself did not like quantum mechanics, as you know very famously, because he didn't believe in this probabilistic interpretation. So he became the great opponent of quantum mechanics later. Now, S.N. Bose, of course, is more of an enigma in the sense that his life is not so well written about. And in some sense, though he was a very outgoing person in many ways, but he was also, there were many things which he kept secret to himself. For example, the thing I have told you about the fact that his interaction with Einstein was not very congenial. This he never told anybody. It came out only much later in his life when he was talking to a very close friend. It's only that little small statement. So the point is that, but it is almost, I think it is clear that he was familiar with when quantum mechanics came with the papers of Heisenberg. He heard Heisenberg's talk, Schrödinger, and so on. Schrödinger's work must have heard Schrödinger's talk also, and so on. But somehow he didn't think it worth getting into. In fact, what happened is that after coming back to India, I mean, he worked mostly on empirical stuff, okay, and some pure mathematics. But he did somehow, I mean, he had all the equipment to do quantum mechanics. In fact, some of the basic ideas he had already guessed, and he was a very accomplished mathematician. So the mathematics needed for that, many people had to learn linear algebra and so on for that. But he knew all those very well. The fact that he didn't work on it probably indicates that he didn't like it. He didn't believe it. And there are hints in his work. But on the other hand, there are also hints that there was a third paper which he wrote in Europe, which finally didn't get published because Einstein refused to publish it, which had more speculations. And those actually contained some of the seeds of quantum field theory also. But he had his own way of thinking. Actually, it's very difficult. Bose was such an intuitive physicist. It's very difficult to replicate his way of thinking. He was in that sense, he was more like Ramanujan. I mean, Ramanujan, if you asked him to prove his results, often he couldn't. He could just see the result. He could just understand it. And if you asked him the intermediate steps, he had to think and make them up. Bose, in some way, had that similar facility. He could see the results. He could see what was done. But if you asked him to rigorously prove it, he could not. And there are intuitive scientists like that. So that's, I would say, so let us say Planck was an absolute classical mold scientist. He understood and sort of worked out every step of where he went. Einstein, of course, was Einstein. I don't even feel qualified to talk about it. And Bose was at the other end. He was an intuitive scientist who got his results. But somehow, I don't think he liked this idea of probability too much either. Anyway, can't tell you more.
Okay. Thank you. Thank you, Sruddha. So,
I can see a lot of questions on it, and please pick up from the live YouTube live stream. I can see many questions.
So there are many.
Those are actually
because also we are also running out of time. Can we extend it a bit?
I don't mind. I'm sitting at home.
One question asked by Deepan. Deepan said, sir, one question. As you are well aware of the history of science, can you please say whether the Wikipedia quote that spectroscopy originated in India is true?
That what originated in India?
Spectroscopy.
No, it didn't originate in India. Spectroscopy began with the spectrum, with the discovery of the spectrum. Okay, so that was by Newton, and we all know that.
Okay, Onamda, can we take some more questions? Quick questions. This we have debated a lot, Umrangshu, that why Professor Bose never got selected as for the Nobel. This, I think, is a much debated one.
Yeah. Well, the Nobel Committee makes its own choices. There are many reasons why they make their choices. I think part of the reason for the Nobel Committee, I think so, is part of it, as I said, because Einstein took a lot of the credit. And we must remember that in those times, it was difficult for people to even believe that somebody from a remote place and with a remote background like S.N. Bose would be able to do so much, to see so much which other well-known people were not seeing. So there was some racism in it, some simple disbelief. And later in life, this happened after Bose's death. A very famous Nobel laureate, in fact, started writing papers saying that Bose had found his discoveries, as I said, by serendipity. He had actually made 2 compensating errors and got his result, which, as I think I have shown you, was not at all correct. It was completely wrong, and Bose knew perfectly well what he was doing. So, and that kind of thing has happened. I have heard from, I'm only quoting. So Professor Partho Ghosh, you must have heard of him. Professor Partho Ghosh was Professor S.N. Bose's student, I think his last student. So he was fairly close, and he had heard many things from Bose directly. So Professor Partho Ghosh thinks that Shoten Bose, of course, was very close to the Indian freedom movement. In fact, their classmate Shoilen Ghosh was actually a revolutionary who had actually built bombs and so on. You will find that perhaps in Anirban's book. So he was always suspected, and maybe the British government had, they have long reach. So maybe they didn't want either Meghnad Shah or Shoten Bose to get the Nobel Prize because they felt it would give them a lot of importance and maybe somehow help them to further the cause of Indian independence. It's only speculated. Of course, they lived beyond that, so they could have been given it later. But we don't know. We don't know that Shoten Bose was nominated for the Nobel Prize a few times, but the Nobel Committee didn't think to give it to him. I think it is completely unfair because if you look at that list of people I have shown you in the second slide, some 16 people, everyone got the Nobel Prize except Shoten Bose, George Gamow, and Pascal Jordan. Now, Pascal Jordan didn't get it because he became a Nazi, and at that time, after the Second World War, nobody was willing to give him a Nobel Prize. George Gamow, people didn't give it to him because he didn't give up his Russian citizenship, and so that was the Cold War period, so they didn't give it to him. There was absolutely no reason not to give Bose his Nobel Prize. Anyway, so the Nobel Committee has done many such injustices.
Okay, so one last question. If we don't have many more in the YouTube live stream, Joydeep Mitro, would you kindly unmute yourself and ask the question? Joydeep?
Yes. Am I audible?
Yes. Perfect.
Yes. So I would like to ask one thing. I have read somewhere that Louis de Broglie back in France did some derivation on Bose statistics before actually Bose did, but he did it in some French papers and got unnoticed. Is this kind of thing true? I think I have read this in some Abraham Pai's book, or maybe I am wrong, but is this thing true that Dabroy also used this same kind of indistinguishability before Bose did?
Well, I have not read this, but the point is that it's unlikely that things which are written in French journals would get unnoticed. Because in those days, everybody in Europe learned French. It was not like in the Russian, people used to write in the Russian journals during the Cold War and nobody read Russian journals. So many discoveries went unnoticed. It was not like that. Everybody knew French. In those days, it was compulsory in Europe to learn French. So it would not have been because it came in some French journals. If the work had been good enough, I'm sure there would have been some other reference to it. Maybe he did work on something. I mean, there were many people trying to work on some kind of statistics.
Yes, back in 1923 or so, I think I have read it somewhere, but I cannot give you the reference. It is some archive paper that I have seen it. So if I can remember the reference, then I will eventually put it. But
it certainly did. Well, even if you go back to 1911, the work of Nathanson was very close to the work of S.N. Bose. But that came out in a Swedish journal and nobody took it seriously. So these things often happen. If you go, you may go back even further and find similar things had been done earlier by other people. Okay, but certainly it didn't make an impact. I don't know about this work, but it certainly did make an impact. If there's any other question,
thank you. Thank you, Joydeep. Anirban.
I think there is a question like can we take that?
Yes. Yeah, from
There is a last question.
So one at a time, please. Anirban, are there any more questions in the YouTube live stream?
I'm just checking because there are many other comments which are not questions as such.
Okay, so you please
Purnamada,
select
if you
one
can
of
see the
these.
question,
Amazing.
you can you can bring it up.
Ornauda, do you want to make a comment or
No,
select
no.
one of the
I
comments?
just said that Tithi Shaha asked a question. We should entertain
Okay.
this.
Okay.
Yeah.
Tithi, please unmute yourself quickly and ask the question. Tithi Shaha, are you with us? Quickly, please.
Yes, ma'am.
Can't hear her.
Tithi, please write your question in the chat box. Meanwhile, Anirban,
Tithi, I'm doing it. Tithi has written, what is the path of totality? Do I didn't understand the question. What is the path of totality?
This looks like a question which you should ask to a religious leader rather than to a scientist.
I didn't understand the question.
What do you mean by that? Please explain. What I have no clue. What is the path of totality?
Tithi, you can write your comment in the chat box.
Well, she has left the meeting.
She has left. Okay.
Okay. Anirban, Dr. Shaha?
Yes, I'm checking the YouTube, but I don't see any question. There are many comments here about Marconi.
Yeah, there are interesting discussions that should be preserved, kind of thing.
So, shall we take one or two, or just go ahead with our program?
Sure.
Anirban?
I think we can hand it over to Vibhasda.
Okay, so let us thank Professor Rai Chaudhary for an excellent talk. I see lots and lots of comments congratulating Professor Rai
Thank you
Chaudhary.
all of you who have liked my talk. Thank you for your comments.
Thank you so much. So I hand over the baton to Dr. Bhattacharya, Vibhash Bhattacharya, for the vote of thanks. Dr. Bhattacharya?
Yeah. Thank you, Molly. Am I audible?
Yes.
Yes, Vibhash, you are.
Okay. Good evening, everybody. Now it's finally the Thanksgiving ceremony. It's our great pleasure to see the webinar, History of Science and Indian Perspective, HSIP 21, become a grand success. At the very outset, I, on behalf of the Department of Physics, West Bengal State University, must thank our Honorable Vice Chancellor, Professor Mohua Das, for her kind support in organizing this webinar. We are thankful to the University Authority for extending all sorts of cooperation and support. We are really thankful to our distinguished speakers, Professor Narayan Banerjee from IISER Kolkata and Professor Srirup Rai Chaudhary from TIFR Mumbai, for giving us their valuable time despite their very tight schedules. Thank you, Professor Banerjee. Thank you, Professor Rai Chaudhary, for delivering two excellent, exciting lectures. I must thank the audience, the students, the researchers, and the teachers from various colleges, universities, and institutes from all over India for joining and making this webinar a success. Our thanks are due to our beloved students and alumni, without whose support and active participation, no event in this department could ever be successful. In this connection, I take the opportunity to thank in particular Sri Shubhajit Rai Chaudhary, one of our alumni, presently at IISCT Shibpur, and Sri Kaustav Das Chakladar, one of our present students, for lending us technical assistance in running the YouTube live stream. At the end, I thank all the teachers and guest faculties of this department for their kind cooperation. Before I finish, this is just to remind you that the link to a feedback form will be given in the participants' WhatsApp group just after this program is over. Also, it is being given in the chat box of this meet. Please check the link and fill in the form to receive your EP certificate of participation. Thank you all. Thank you all once again. Bye. Thank you.
Yes, let us please, Ornavada, please share the link for the feedback form.
Give me a minute. Okay, I'm just doing it.
Yeah, and we can all open our videos, to express our Thanks
I've
to
given
the,
the link
Thank
for
you.
the feedback form.
Thank you.
So you fill it,
Please,
you get your
yeah,
certificate.
please
and
open your video
be
so that
sure
we can express our gratitude to the
particularly the
speakers.
YouTube stream watchers, you cannot copy it from here, but I will give it to the WhatsApp group. Okay, in both the WhatsApp group, I'll supply the feedback link. So if you can't copy from the message window, you can get it there from in the WhatsApp group. Okay.
Thank you to all the participants. Thank you, Srirubda.
Welcome. Thank you. Invite me.
Ornabda, do we have to keep this meet open?
না কেন না
না।
এবার আমি শেষ করি হ্যাঁ
So let all the participants, the student participants and the others leave.
Okay.
So thank you very much.
Thank you very much.
Thank you, Naranda. Thank you so much.
Thank you very much. All right.
Thank you very much.
Bye bye.
Goodbye. Good evening. Good night. Whatever you
Good
like.
night. Good night. Thank you.
Bye.
শুভজিৎ আছিস
আচ্ছা শুভজিৎ আর কৌস্তব তোমরা দুজন থেকে যাও কৌস্তব আর শুভজিৎ তোমরা একটু ওয়েট করো
এই একটা জিনিস বলো তো এই যে ডিসকাশনটা হচ্ছে লাইভ স্ট্রিমের তলায় যেটা নানান রকম লোকে কমেন্ট করেছে না সেগুলো খুব ইন্টারেস্টিং লাগছে মানে সেইটাকে একটা জায়গায় কপি করে
ক্যান ইউ ক্যাপচার দ্যাট
সেটাই বলছি সেটাকে রেখে দেওয়া যাবে সেটাকে নানান রকম করেছে আমি দেখতে পাচ্ছি বেশ একটা ডিসকাশন হয়েছে
I could have gone and on listening.
সেটা আমি লাইভ স্ট্রিম শুনে না অতটুকু জানি না শুভজিৎ তুমি জানো এটাকে কি রেখে দেওয়া যায়
এটা মিটিংটা বন্ধ করে এটা তো লাইভ স্ট্রিমে अवेलेबल থাকবে স্যার
লাইভ স্ট্রিমে अवेलेबल থাকবে না মানে পরে লাইভ স্ট্রিমটা দেখলেই পাবো
হ্যাঁ স্যার পরে চ্যাট বক্স খুললেই পেয়ে যাবেন স্যার
হ্যাঁ তার মানে হচ্ছে আমি যখনই কাউকে একটা লাইভ স্ট্রিমটা তো রেকর্ডেড হচ্ছে তার মানে এটা তো পরবর্তীকালে আমরা আমাদের ওই ইয়েতে পাওয়া যাবে মানে এই
ফিডব্যাক ফর্ম কতক্ষণ ওপেন থাকবে ফিডব্যাক ফর্ম
বলো তোমরা কতক্ষণ পর অফ করবো
হাফ অ্যান আওয়ার দেবো হাফ অ্যান আওয়ার
লাইভ ইউটিউব লাইভ স্ট্রিমে কমেন্টে জাস্ট কাট মানে কপি পেস্ট করে দেওয়া যায় কপি করে পেস্ট করে দেওয়া যায়
আচ্ছা
এটা ওনারা তোমার কাছে মেইল আসবে তুমি মিটিংটা হোস্ট করছো না যে মিটিংটা হোস্ট করছে তার কাছে চ্যাট বক্সে যে লেখাগুলো আছে সেগুলো একটা আলাদা মেইল আসবে একটা আসবে হচ্ছে রেকর্ডিংটা মেইল আসবে আর এইটার একটা মেইল আসবে
আচ্ছা
যেখানে লেখা থাকবে যে চ্যাট বক্স
আচ্ছা ঠিক
তোমার ওই যে ইমেল সেখান থেকে তুমি করছো সেখানে আসবে আচ্ছা আমি দুটো মেইল আসবে
find a few more participants still hanging on. The webinar is over. Kindly leave the meeting. Thank you all. Thank you. Yes, I'm Mondol. Thank you.
চলো আমরা বেরিয়ে গেলাম
ওয়েট কর একটু শুভ দাঁড়া ওয়েট কর
ভালো হয়েছে টকটা
রিজন একটু লেটার পাঠিয়ে দিও ওদেরকে দুজনকে
বলুন
এদেরকে ধন্যবাদ জানিয়ে একটা লেটার পাঠিয়ে দিও
স্যার লাইভ স্ট্রিমটা এন্ড করে দাও
অনির্বাণ আমাদের দুজন স্পিকারকে থ্যাঙ্ক দিয়ে দুটো মেইল পাঠাতে হবে
স্যার লাইভ স্ট্রিমটা এন্ড করে দেবো
হ্যাঁ অবশ্যই
হ্যাঁ
থ্যাংক ইউ
এটাকে এডিট করতে হবে তাহলে আমাদের হ্যাঁ
লাইভ স্ট্রিমে ভিডিওটা অন্যভাবে একটু এডিট করতে হবে দুদিকে একটু ট্রিম করতে হবে
এটা তো কে এখন লাইভ স্ট্রিমটা চালাচ্ছে
এখন বোধহয়
সেটাকে